One thing which I've always found really gobsmacking, to be honest, is that if you've just got a flask of hydrogen and CO2 and you warm it up a little bit, shake it, and it's actually thermodynamically, in terms of the energy released and the entropy of the universe, it is more stable to make cells out of those two gases. You're effectively turning gases into the molecules of life. The question is, we only know of one form of life, and all life on Earth is basically the same insofar as it's carbon-based. It's cellular, it works in water. An algal cell floating in the ocean has the same machinery at a cellular level as one of your kidney cells. It's still got the endoplasmic reticulum, it's still got the nucleus, it's still the nuclear pore. It's all that machinery.
That's such a cool sentence. That's such a cool sentence.
Crazy.
Yeah, it's really worth restating how cool that is.
Yeah, can try to look at life on Earth and understand why it's this way. I mean, the subtitle of the vital question was, why is life the way it is? And it's just a really interesting question. Did it have to be this way, or could it have been a completely different way? And the more I've thought about it, the more I've thought there's really good reasons why it's this way.
Yeah. Nick Lane is a biochemist, best-selling author, and arguably the most important thinker alive when it comes to the origin of life. His radical idea that life and even consciousness began not in a primordial soup like is stated in most biology textbooks, but in the rocks of the ocean floor, where simple gases like hydrogen and carbon dioxide met gradients of charge to create the first living cells. He's written Transformer, The Vital Question, Power, Sex, Suicide, books that have reshaped how we think about biology, energy, and evolution. Bill Gates called his work mind-blowing. Richard Dawkins said it changed his view of life. This is what the Giant Shoulder podcast is all about. Subscribe if you want to understand why every single one of your thoughts might just be the ghost of an ancient proton gradient.
Why does one cell want to become two cells, which is a famous question. Why would things grow at all? Where does that impetus come from? It simply comes from the Earth being a giant battery with all the electrons down there coming out, driving this reaction. Doubling is almost inevitable in a hydrothermal system. Growth is just an outcome of these two phases that are constantly reacting with each other.
I get the sense that you think electricity and bioelectricity might be the key to some of biology's largest mysteries at the moment, and it's been relatively unexplored. Would that be correct to say?
Absolutely, yeah. Why would potassium ions or sodium ions or calcium ions coming into a cell give rise to a feeling of anything at all? What is a feeling in physical terms? Is there a kind of a quantum of a feeling in a bacterial cell trying to integrate its state in relation to the environment as the readout of your metabolic wetware, charge and movement of charge on a membrane? Yes, I think that they would have feelings in that sense, and it may be as simple as good or bad, go or stay. I don't really subscribe to the idea that the universe is conscious, to the kind of panpsychism ideas. I tend to think of it as primarily as a process of life, of living things, and dependent on the substrate of living things, so the wetware of metabolism and so on. And so an AI, even if it's robotic and self-aware and all of those things, is not necessarily going to have, it's a very different substrate. It's not necessarily going to have feelings in the way that I suspect animals would.
Yes. Have you thought much about the future of AI and science, and really where the huge advancements could occur? Nick Lane, you have a very vivid picture in your head of where life first emerged on this planet. Paint that picture for us. Really set the scene.
Well, the kind of place that I think about are deep sea hydrothermal vents. And as soon as I say hydrothermal vents, most people probably, if they have a picture in their mind at all, it would be of some kind of smoke coming out of some chimney. These are the kind of things that we see on television. That's not actually the kind of vents that I have in mind. The ones that we see today, and some people will be familiar with them, they are kind of tottering pinnacles of limestone, with all kinds of amazing kind of doodles of rock. I like to think of them as a Gothic cathedral almost. It's a different kind of system. It's actually produced by interactions between rock and water, so it's not volcanic at all. and they're not obviously gushing out hydrothermal fluids into the oceans. Now, inside them, there isn't a chimney, but you've got this labyrinth of interconnected pores. And the pores themselves, I mean, with a little bit of imagination, you can see them as cell-shaped. They are kind of pockets with a barrier around them. And you have continuous flow going through. So there's two things that I would really take away from that, having kind of reflected on these things for decades now. There's two things. One is the structure. You've got a cell-like structure, and the other is flow, continuous flow past or over or through this cell-like structure. Not a really harsh flow, but just a continuous flow. So a continuous reactivity. And at the origin of life, you've got these reactive fluids which are being brought together with a structure which is facilitating their reaction and effectively converting gases into gases like hydrogen and carbon dioxide into organic molecules. And one thing which I've always found really gobsmacking, to be honest, is that if you've just got a flask of hydrogen and CO2 and you warm it up a little bit, shake it, and it's actually thermodynamically, in terms of the energy released and the entropy of the universe, it is more stable and a higher entropy overall to make cells out of those two gases. It will release energy into the universe if hydrogen reacts with CO2 to make cells.
It's amazing.
That's just thermodynamically favored state. And there's barriers. It's not going to happen very easily. But in these kind of events where the structure and the flow are breaking down those barriers, you're effectively turning gases into the molecules of life.
This is a different view than most people might have read in their textbooks. I remember back to my college lectures, and you hear about the primordial soup, right? The idea is like this beam of lightning, this initial spark, which might have just synthesized different chemicals, as you say, in the environment, and you get those original amino acids that eventually form RNA and all of the rest. How does your view differ, and why are you more confident in this hydrothermal vent idea?
It's a strange thing, but almost everybody's heard of the primordial soup, and,
Yes.
and most people are familiar with this idea of what was known as the Miller-Urey experiment, which was flashes of lightning, so electrical discharges in a flask, and that flask contained hydrogen and ammonia and methane and water and not a lot else, and the flashes of lightning forced them to react and form these amino acids, and this was back in 1953. This was really the first serious experiments done on the origin of life, and it had a very specific hypothesis behind it that the Earth's atmosphere would be something like Jupiter, which the gases were known roughly at the time. And so Stanley Miller had done these experiments, and they worked astonishingly well. Now, since then, there's been all kinds of squabbles about what was the Earth's atmosphere really like? Was it these Jovian gases or not? And the answer is probably not. Probably it was more like CO2. The field has moved towards chemistry, for example. You start with cyanide and you use UV radiation, and then you've got a continuous reactivity there as well. The problem I have with all of this is you can make the building blocks of life, but then they kind of sit there, and the question is, and now what happens? What animates it really?
Yes.
What makes them react with each other? And when they do react with each other, and the pathways required to make them looks nothing like biochemistry as I know it. And so you've partly answered the question. You made the building blocks of life, but they're inanimate almost. And the question is then, so how do they then come to life and invent all the metabolism and come up with a genetic code and all the rest of it? So they've not really answered the question. The other way of looking at it, which is my way of looking at it, as a bunch of people around the world see it this way, and it's always been disfavored by chemists because it's basically difficult chemistry. But start with CO2, start with hydrogen, start with the kind of catalysts that life uses. So iron sulfides, things like that, metal ions, things like nickel and molybdenum and so on. Start with those and potentially with some structure where you've got ion gradients across membranes, proton gradients. And what do you get? Well, the answer is you get the simplest kind of carbon-based molecules, Krebs cycle intermediates slightly more technically, but basically these are the molecules that are just carbon, hydrogen, and oxygen. And from there, life makes amino acids, and we can do these things in the lab. And from the amino acids and sugars, you make the nucleotides, and we can do not all of it, but some of those things in the lab. So the idea, let's call it imagination still, but this is the aspiration of what we will be able to do in the end, is you start with CO2 and hydrogen. And before you've got any genes or any genetic information or really any proteins or enzymes or catalysts of that sort, you get a kind of network of reactivity which foreshadows metabolism as we know it. And so all the stuff that's happening in your cells right now was happening back then in a hydrothermal system, just because it's thermodynamically favored chemistry. That's what happened when you get these molecules to react. So we're still a long way from doing that, but over the last 10 years or so, the evidence that it's not completely unreasonable has got a lot stronger. I think a lot of people would have reasonable doubts still, but certainly it's much stronger rather than weaker. And once you've got there, then the first genes, all they actually need to do is amplify flux through this pre-existing metabolism. Whereas if what you have is information first, well, what do the genes have to do? They then have to encode all the metabolism, and that's really tough, actually. That's not something that anyone's ever got near to doing.
Right. You have a great quote in the book, which I think sort of echoes what you said in your book, Transformer. The fit between the geochemistry of alkaline vents and the biochemistry of methanogens and acetogens is so close that the word analogous does not do it justice. It's really remarkable that you're saying that the earliest system was 100% geochemistry, was environmental components interacting with each other. And then somehow we got this local biochemistry. How do you get that local chemistry not to dissipate to zero? How does entropy not just do its job and just squash all chemistry that emerges? How long can that chemistry exist locally without just being crushed? Do you know what I mean?
Yeah, I mean, the answer has to be indefinitely. So the question is that real? So I'm talking about these cell-like compartments, this labyrinth of interconnected micropores and so on. If you think in terms of the thermodynamics, I said it's favored to get whole cells, but there are certain molecules that are more favored than others. The ones that are most favored are amino acids and fatty acids. So these are the ones that if you're reacting CO2 and hydrogen, you should get most of those things. You should get fatty acids and amino acids. And things like nucleotides to make DNA or RNA are a bit more difficult and complicated to make. So fatty acids, we and others have shown that if you put them under those kind of conditions, they will spontaneously form a bilayer membrane, very similar to the membranes you see around cells today. So they will form what I'd like to call a protocell. It's basically a kind of a membrane around an aqueous space. And they are pretty stable things. How long will they last without dissipation? It's difficult to know. But what we're really looking for is not a system which is never going to dissipate so much as a system which is continually being replenished. So you have dissipation continuously. You're going to be losing things. They're going to be reacting, moving on, being flushed out of the system. But you're also because of this continuous flow, you're continually making more of them. And the ones you make more of are the ones which are the most favored. And so you're effectively, you're in a steady state that you're continually making these things and continually losing them. And on balance, the kind of steady state equilibrium is you've got cell-like things, and those cell-like things are continually potentially converting more of these gases into more interesting things inside them. So as soon as you've got a cell-like thing, then you're beginning to prevent the dissipation already. Right. The membranes themselves will tend to stick to the mineral surfaces. So they're not going to just get flushed straight out into the ocean. They physically just sit there inside. I imagine them almost templated within the pore as a kind of a pore-shaped vesicle, protocell sitting inside it.
Is that possibly a good argument for why you think that life emerging is so much more probable in the hydrothermal vent system? Because if you have a primordial soup, it seems a lot less likely that it would ever persist consistently and ever be able to persist at a greater rate than it would just be dissipated if you don't have these geochemical structures which are creating protocells and membranes and local chemistry, that it would be much more likely it would dissipate to zero within this soup? It's just too chaotic, it's too messy.
I mean, even within a soup, you're still going to have a formation of new materials and a kind of elimination of older materials. So you'll still have some turnover, but it's not very obvious where the structure comes about,
Yes.
or why something would grow.
Yes.
So if you think about, what cells do now is they grow, they double. One cell makes 2 cells, makes 4 cells, and so on. And inside those cells, you've got the genes, and the genes are made of DNA, and the DNA is being copied, and each daughter cell gets a copy of it, and so the DNA also is going 1 to 2 to 4 to 8, and so on. Now, that's a form of doubling as well. It's just more exact than a cell kind of just falling in half, you might say. And I mentioned these fatty acids, membranes, protocells. They're very dynamic things. They do fuse together and divide in half and so on. So there's no problem with them making copies of themselves, very approximate copies, so long as they're able to grow. So why would they grow? Well, they grow because you're continually replenishing the reactive requirements from the environment. And so you're continually making more stuff. And that stuff is apportioning itself and dividing and fusing. And on average, you end up with making more and more all the time. So growth is really coming before the more exact forms of growth, which would be replication of DNA. But
Right.
First of all, you need to be making more stuff all the time. Now, that's what I don't see happening very easily in a kind of any soup-like system. What is bringing it together and making these things make copies of themselves? I just don't really see the driving force there. Whereas in a hydrothermal vent, you can't escape the driving force. You're constantly converting this flow of stuff into more of yourself.
That makes complete sense to me. Explain the alternate hypothesis of this RNA world. If metabolism wasn't first to emerge, the original idea was that RNA emerged, and that was both the information scaffolding as well as the catalytic engine, that it could replicate itself. Firstly, I don't really understand how it's able to replicate itself with any level of fidelity. It seems like you just make a lot of mistakes and then it might go to zero. But explain that a little bit. Explain that hypothesis first and why you think it's less likely.
So the hypothesis is beautiful, and it comes about really from a chicken and egg problem with DNA, because
Right.
DNA is the genetic code, but it's basically inert. And what it does is it codes for proteins, and proteins do all the work, but they're coded for by DNA, and they can't make copies of themselves. And so there's this question, which came first, the DNA or the proteins? And actually there is an intermediary, which is RNA. So DNA makes a kind of carbon copy of itself almost, which is called RNA, which is a short form of it. And that codes for the protein. Well, RNA also can fold into interesting shapes, and has catalytic potential. And so it can do partly what a protein does and partly what DNA does. And so there was this idea that before you had proteins and DNA, you had a world in which RNA was copying itself and doing chemistry. And it's, it's a simple idea.
Yeah.
It's never been demonstrated to be true, but there've been lots of people working on, can we make a ribozyme, so an enzyme which is made of RNA, that's capable of copying itself. And to some extent, it's been done. It tends to be this one will copy a different one, which copies a different one, and you can go in what's called a hypercycle, and eventually things will copy themselves. But it leads to downstream problems, and in terms of how do we get to where we know the end point is from there. So what would an RNA world have to do? Well, it would have to invent cells. It would have to invent metabolism. It would have to invent proteins and the genetic code whereby DNA codes for proteins in the end. So these are the things that the RNA world has to do now. And actually, almost none of that has been demonstrated in the lab as being real. It's actually almost being completely ignored. So the challenge for an RNA world really is to get from there to life as we know it. And there's kind of an assumption, and it's a very lazy assumption, that if you've got genes, if you've got RNA which can copy itself, you've got genes. And if you've got genes, well, then natural selection can happen. And once you've got natural selection, you're away and you don't need to explain the rest. It's just a detail. It's really not a detail.
Right.
It's, there's selection can work in multiple different ways, but there's also things it can't do. And there are famous things that it can't do. And one of the more famous ones is come up with complexity, because the point about little bits of RNA, little genes which are copying themselves, is they will tend to get smaller and faster. They're basically selfish. They will copy themselves furiously at the expense of any kind of cooperation or altruism, you might say. Cells put them together in the same bag. So now all of these selfish bits of RNA, well, they can't get out of the cell. They've got to cooperate in some way and help the cell to grow. But now we're in a very different context.
Right.
So the end points depend on really what the starting point was. And if the starting point is you're already in cells and you can already generate the materials needed to make a gene, then you're all in the same boat, and selection is going to operate very differently to if you've got what people think of as a naked RNA world. Naked meaning lots of little genes all kind of squabbling and fighting between themselves, but not inside cells.
Right. Well explained. I just love the way you do scientific communication. I think it's so well done. While ChatGPT can be great, I've found that specifically in areas that are pretty uncertain, like all of neuroscience, that it can also get things horribly wrong, and it's just not a reliable source of scientific information. This is why I have personally used Consensus.ai for over a year now, and I literally would not be able to do my job without it. Think of Consensus as the ChatGPT for science, trained on actual research papers and designed to give you differing perspectives when something isn't really as clear cut. Let's test this out with a really controversial one that basically no one in the field can agree on. Is serotonin related to depression? As expected, so very mixed, although I don't know if I've ever seen it quite this mixed before. So it gets 69% yes, 6% possibly, 6% mixed, and 19% no. You can break down where it's getting these scores from, what papers, what year. Again, it's just weighting the evidence in such a clever way so you can understand what you need to understand. And a new feature that I absolutely love is that they have threads introduced, so you can probe down into deeper levels. What is the efficacy of SSRIs? Again, super controversial, really interesting though, and a really important question. And threads just allow you to go deeper and understand that nuance at every single level. It's really why I love it. It's integral to my job. And the amazing news is that you can try out Consensus.ai for a full year completely free with the code Giant Shoulder in the description. That's right, I didn't say a 7-day free trial where you forget to cancel and suddenly you're $100 down. No, this is a full year, so there is literally no harm in trying it out. You just have to have one scientific question that you want a good answer to. Maybe it's how much creatine I should be taking in the morning, or should I be taking it in the morning or at night? Is consciousness fundamental, or why is the star-nosed mole just objectively the best mammal? Questions that keep you up at night. There's no better tool than Consensus.ai. I love that they're a sponsor of the channel, and I couldn't be more appreciative. Please go try them out. It really supports what we're doing. Okay, so what we have is we have carbon dioxide and we have hydrogen, and they're fusing together with the work from free energy produced at hydrothermal vents into organic matter. Is that right so far?
Yes, yeah.
Okay. And then that evolution of that system, is that going to drive the evolution of the information, the RNA and the DNA? Is that metabolism going to drive that evolution? Are they co-evolving in some way?
Yes, I mean, this is some of the most beautiful work that I've been involved in over the last few years. These ideas were really coming from Stuart Harrison in my group. And for decades, actually, we've known that there are patterns in the genetic code. And these patterns suggest some link with metabolism and some link between the genetic code. You've got what are called codons, and anticodon. So the codon is a triplet of 3 letters in the genetic code, which codes for 1 amino acid in a protein. So if you've got a stretch of DNA or RNA, you think of it in groups of 3. You can think of it as a long ticker tape of letters grouped into units of 3, and each unit of 3 is called a codon, and that codes for 1 amino acid. If you zip up all the amino acids, then you get a protein, and the protein, the sequence of amino acids in the protein depends on the sequence of letters in the DNA grouped into these brackets of 3, which is the codon. So that's the genetic code in a nutshell. And the thing which is odd, there's various patterns, and one of those patterns, for example, is that the first letter of this codon corresponds to the position in metabolism, more or less, especially if you look at it as, let's say, metabolism starts with CO2 and hydrogen, and you go through metabolism as we know it. How long does it take you to get to this amino acid or that amino acid? Some of them are closer to the starting point of metabolism, some are further away. Well, that corresponds to the first letter of these codons. You can plot a graph, and the ones which are close to the beginning of metabolism, they all start with a G, and the ones which are furthest away, they've all got a U at that first position. So it's kind of odd. What is it? How do we interpret that? But it's there for sure. The second position corresponds to the physical properties of the amino acid that's coded for. So especially, is it hydrophobic or hydrophilic? Is it water loving or water hating? And the more hydrophobic letter that's there, base that's there, so the least water loving one corresponds to the more hydrophobic amino acid. So the two things sit together. They're physically comfortable together. And correspondingly, the other way around, the more hydrophilic one, so uracil is the most hydrophilic base, goes with the most hydrophilic amino acids. So it just looks like they're nestling up together, snuggling up together physically. And then the third position is about the size, just how big are these things that are nestling and snuggling up with each other. So all of that says this, in the broadest brushstroke, the genetic code has got patterns in it that suggest there's a link with metabolism, and these things were interacting directly for physical reasons right at the beginning. And what that suggests in turn is that metabolism came before the genetic code, that these things were co-evolving, really, as you put it. Exactly how? I mean, we've been trying to do models on this kind of thing to show that you can introduce a random sequence of RNA, and over multiple generations, it will eventually end up coding for an optimal peptide, optimal protein. Is it real? Is it true? All you can do with a model is just show that it's systematic, really, that this thing is possible under these conditions.
Right.
So it's hard to know, but what the really exciting thing about it is that information, the origin of genetic information, has been such a problem in biology that brilliant minds like Paul Davies and Sarah Walker and people like that are trying to call on some unknown law of physics to explain where information is coming from, whereas in fact all you really need is physical interactions that say you've got a random stretch of RNA and it's going to template through physical interactions a non-random sequence of amino acids in a peptide. If you zip them all up to make that peptide, then the sequence of the peptide depends on the sequence of the amino acids. Sorry, the sequence of the letters in the code underneath. And so then you have selection as we know it in a cellular context with a metabolism as we know it. And in this case, you really do have selection for greater complexity. So it may not be true, but it has huge explanatory potential, and it's consistent with everything that we know about the genetic code.
Do you think we'll ever conclusively prove it? Is there an experiment that can be done in the lab or on a computer with some advanced AI and computational models, and then we'll be like, bam, that's it. We have solved it conclusively.
No, I don't think we ever can do that.
Right.
In principle, we could. It certainly wouldn't be as simple as ever simply proving that this is how life started, because that's a kind of a historical question. The only way it could be proved that this is how life started would be to disprove every other hypothesis as to how life could have started, to say, no, at this point it gets stuck, no, at that point it gets stuck, and so on. So I don't think we're anywhere close to doing that. If there is only one path to go from prebiotic chemistry of a specific kind to cells as we know them, and everything else cannot possibly work, then it would stand to reason that life must have followed that path.
Right.
But I think we're a long, long way away from doing that. But I think that it's a long path, and maybe there's multiple ways through it. But if you start at the beginning and you specify an environment, then you're obliged all the way along to say, okay, well, if this is true, then here's what I should get, and if that's true, then here's what I should get, and the end point has to be where we know it. And if you can't get there, then your ideas are obviously wrong.
Right.
So I was criticizing the RNA world. Can this RNA world invent metabolism? I think the answer is no, but I'm not going to try and prove that, because that's their job. People who believe that it can, that's their job to prove that it can.
Has anyone came up with an alternate algorithm for life, like a system that seems to work from the start based on the environmental components that does exist? Or like, did it have to be the way it is?
I think that depends a great deal on what you would mean by life. So if you were to talk about, say, computational forms of life in silico, then it's probably been done already. There will be things that are lifelike and can evolve, and so in that sense, it's trivial and it's being done. If we're talking about organic life or life on a planet, so it's not actually brought into existence by someone inventing computers and all the circuitry and everything that goes with it. If you start with a planet or a moon or space or a sun or wherever it is, any environment in the universe, how does life bootstrap itself up from effectively inorganic chemistry to whatever life might be? I think there are serious constraints on what can be done and can't be done. And I'm sometimes accused, and fair enough, of being kind of narrow-minded, and the criticism that will come is an infinite universe, an infinite number of things can happen, and you've got a little brain, so and you can't possibly imagine all of the things that could be happening out there. So stop being so arrogant and dismissing the possible amazing nature that life could have. It may be true.
Harsh criticism.
Well, I don't think it's a scientific criticism, because science is really about, can you test things? And it's no good just saying, oh, well, it may be amazing. And that's not really science.
Yeah.
The question is, we only know of one form of life, and all life on Earth is basically the same insofar as it's carbon-based. It's cellular. And some people will immediately say, but viruses aren't cellular, but viruses depend on cells to copy themselves. So in that sense, we can reduce it back down to life is cellular. It's carbon-based, it works in water. And so then the question is, did it have to be that way, or could it have been some other way? And the more I've thought about these things, the more I think there's very good, strong reasons why it is the way that it is. Carbon is extremely good at this kind of difficult chemistry, and it's extremely common. It's one of the more abundant elements in the universe, and it's far better at that chemistry than, say, silicon is, and it's far more abundant than silicon is. And on Earth, silicon is much more abundant, but all life is carbon-based. It kind of says, forget about silicon, it's not the answer. For water as well, it's an astonishing solvent with properties that we barely understand even now. The way that it interacts with proteins, the way that it interacts with membranes, with transfer of protons. It does all kinds of things that most other solvents just don't do. And again, it's abundant. Hydrogen and oxygen are abundant, and water is abundant. So just on a statistical basis, we're likely to be dealing with the same chemistry anywhere else in the universe. And then the question is, under what range of conditions will you be able to react CO2, which is again the dominant form of carbon, into organic molecules? And that range is not huge. You're dealing with, between, more or less the range of the freezing to boiling point of water, and not much more. Under those conditions, you will get organic molecules. So it may be limited, but I think in some sense the onus is on the people who think that life could be any way you want it to be, to say, okay, well, here's how.
Yes. Yes.
I think we can try to look at life on Earth and understand why it's this way. I mean, the subtitle of the vital question was, why is life the way it is? And it's just a really interesting question. Did it have to be this way, or could it have been a completely different way? And the more I've thought about it, the more I've thought there's really good reasons why it's this way.
Yeah. If you knew for sure that there was carbon dioxide, hydrogen, water, and some sort of proton gradient on a different planet, would you then say with pretty high certainty that you think there's life on that planet?
I would be optimistic. I would add another couple of things in. I mean, I'm talking about continuous flow hydrothermal type systems. So what does that require? That requires what I'd like to think of maybe a bit romantically as a living planet, which is to say a geologically active planet, which is to say the crust is turning over continuously. And what that's doing, so on Earth, basically all the iron has gone to the core and to the mantle. And so the Earth is a giant battery. Iron is very electron rich. The atmosphere and the hydrosphere, so the oceans and so on, are relatively electron poor. Volcanoes are outgassing stuff, but the temperature of volcanoes means what they're putting out is mostly carbon dioxide and water vapor and things like that, not hydrogen and ammonia. So it's water and CO2 that's coming out of volcanoes mostly. So relatively oxidized because of the temperature and because of the sun. So you've got a battery. The outside is electron poor, the inside is electron rich, and the places that connect them are the hydrothermal vents, and that's where all the action is happening. And if that reactivity begins to cease, and it would cease if you're not turning over the crust, because you know if you don't have plate tectonics of some sort, then the processes I'm talking about, effectively the water is reacting with the rocks. The technical term is serpentinization, but it's basically rock-water interactions. That reaction would go 5, 6, 10 kilometers deep in about 1 million years across the entire surface of the Earth, and then it would stop. And so to get it going again, you need to be subducting some of this crust down into the mantle or even lower, and bringing up fresh mantle rocks to the surface. So you've got what amounts to a living planet. It doesn't have to be modern plate tectonics as we know it, but you've got this continuous turnover. And it's really, that system is driven by gravity as much as anything else. It's not really driven by the sun. It's driven by the fact that all the iron went down into the core, and so you've got a battery structure.
And how specific do you think that ingredient list is? I spoke to Dr. William Radcliffe on the podcast, who studies the origin of life and complexity. And he kind of dropped a line, which I thought was pretty shocking, which was he doesn't think life is that unlikely. He was kind of shrugging his shoulders like, yeah, it will emerge when the things are there. Like, how specific is that ingredient list, that active planet that you just laid out?
I would say there would be tens of billions of planets with those conditions, planets and moons, in the Milky Way alone. So common, I would say, among the more common types of planets. But I don't really know. I'm not really an astrobiologist, but I think those kind of conditions would be pretty common. Now, how likely it is that you go all the way to getting cells with molecular machines, with DNA, with, it's very hard to know, but my hunch is it's all favored on a planetary scale is going to happen. And actually my hunch, which I find a little bit scary, is that you would get cells that resemble bacteria, and they're going to be of a similar size. They're going to be carbon-based. They're going to have similar biochemistry. They're going to have similar patterns in the genetic code, not necessarily the same genetic code, but the reasons it's templated here through direct physical reactions. If what you have is a set of conditions that generates metabolism spontaneously all the way up to nucleotides, then you will get the same metabolism and the same nucleotides under similar conditions starting from CO2 elsewhere, and then you'd end up with a genetic code that resembles the one that we have. And I find that quite a scary prediction.
Right.
It doesn't feel a comfortable place to be, but it appears to be the only reasonable prediction for the arguments that I have been making. And I think the arguments are quite strong.
What's most scary about that?
It's the level of determinism. It's a little bit reminiscent of the cosmological constants, that if the strength of the gravitational force or the strong force or the weak force or whatever it is was slightly different, then you would not have a universe with suns in it, with gravity as we know it, with the lumpiness that's required, to form stars, to form the elements, to form a universe capable of giving rise to life. Change those cosmological constants slightly, and you end up with something that never formed stars or whatever it may be. So the physicists have dealt with this by effectively conjuring up a multiverse, where they say, one way of doing it is to say, they happen to be just right in this universe. They would have to be because we're here. But in the next door universe, they could be very different, and it could be a very different place. And the idea of the multiverse is coming from quantum mechanics. It's a fascinating idea. You can make very entertaining movies about it. And it seems to solve that problem of the cosmological constants. It's either that, or there's a fundamental reason for why they are the way they are. Now, let me bring that back into biochemistry. What I'm saying is you start with CO2 and hydrogen and water, and you're going to get cells with a genetic code that resembles ours. It feels fine-tuned to the kind of chemistry that's going to inevitably give rise to the same kind of life again and again and again. So it feels as if the universe has been fine-tuned to give rise to life at the level of biochemistry as well as at the level of the cosmological constants. But here, there's no way that I can call on a multiverse because I'm dealing with the laws of chemistry as we know them. I can't explain the propensity of CO2 to give rise to metabolism and genes in the way that it seems to do by saying, it happens to be this way in this universe. No, these are the laws of chemistry that make it happen that way. So why are the laws of chemistry that way? At this point, I'll kind of shrug my shoulders and hand over to the physicists. But
right.
I do find that level of determinism. You may just as well say God did it.
Yeah.
I would say, and I'm not a religious person, but I would tend to use the word God and thermodynamics almost interchangeably to reflect forces that are acting on how substances behave in ways that I don't really have a clear understanding of how those forces came to be.
Yeah. Omniscient ways our silly monkey brains didn't evolve to understand in any way. 2025 is the year that me and you are going to fix our sleep. Now, that does not mean that we need to go full Brian Johnson on it, but one thing we can do that's super easy is to buy the highest quality sleep mask on the market, and that is Manta. I've been blown away by how much better I sleep with one of these on. It's just a fact that people are not sleeping in completely dark environments, and studies show that affects sleep quality, time to get to sleep, and increases the fragmentation of your sleep. I have tried other sleep masks. I first bought one on Amazon last year for like €5, but the problem is they're just really poor quality. They don't really block out any of the light, and you can't adjust them to your planet-sized head. Manta is fully adjustable, so it literally will fit all of the strangest and weirdest size heads out there, like mine. The Manta mask is literally completely blackout. I have studio lights coming at me from here, and I can't tell the difference. It is absolutely pitch black. This is the perfect environment that you need for sleep. Manta honestly feels like you're being cuddled by a cloud. I actively enjoy and look forward to putting these on each night. I just realized how boring that makes my life sound. I sleep with Manta every single night, and I've seen direct improvements in the quality, duration, and how rested I feel when I wake up. My Whoop data seems to agree. I also bought one for my girlfriend, and she also loves it. Manta have a bunch of different sleep masks on their website. I have tried the normal sleep mask as well as the sound mask. I like to listen to audiobooks at night, so for that reason, the sound mask was actually really, really good. For some reason, my girlfriend doesn't want to listen to how reality is a perception at 11 o'clock when we're trying to sleep, so this was a really good solution for that. It's also incredibly comfortable. But as I said, I think for most people, like 90% of people, the normal ordinary mask is going to fill their requirements. Super comfortable and completely adjustable. Literally is just a really high quality, well made product. It's the best on the market. Manta are giving my viewers 10% off their first sleep mask. They ship internationally and they also offer a 60-day free trial. That's 59 of the best nights of sleep you've ever had. I literally promise that. But if for any reason you aren't satisfied, you will get your money back, no questions asked. I really couldn't recommend more if you're looking to do something to improve your sleep. A sleep mask is the lowest hanging fruit. It's so simple and easy to apply, and I think it will benefit your life and overall health, and I could not recommend Manta more. It's such a strange idea that if we ever did encounter life from a different planet, it actually might not look too different from us. That idea is very strange because I think
Well, it could
years of
look very
movies have
different.
primed that difference, right? Primed
Yeah, yeah.
Alien is something else different to us.
You know, films like Alien, sure, it's very different to us, but it's obviously an animal with
Right.
a life cycle and reproduction, and so in that sense,
Yeah, it's not
it is
too.
very similar to us. And so you could end up with life forms that are carbon based that don't look much like us, but which actually function in a very similar way.
Yes.
So, but yes, I would say that the likelihood of life being carbon based, having a metabolism that resembles ours, being cellular, with the cells being of a similar size, there's all kinds of reasons to think that's just going to be the most favored system that's going to appear most frequently
Right.
in the universe.
So cool. Okay, so we have metabolism and some primitive form of information and DNA. What's the next invention to get to a cell? What did biology figure out next?
Yeah, I think most of what I've been talking about was happening in things that you could call a cell anyway, which is to say it's cell-like in that it's got a bilayer membrane around it. It's
Yeah.
capable of growing by, I would say, falling in half rather than going through any fancy form of cell division. But nonetheless, that's relatively easy for these things to do. You can watch it under the microscope in real time. So before you got to genes, these systems, I think positive feedbacks or autocatalytic loops, however you want to frame them, are capable of making it more complex. But I don't think that it has real evolvability in the way that an evolutionary biologist would think of that, which is to say, you can't change the environment and somehow it fights to remain the same way that it was. It's a system which depends completely on the environment that it's in. So you change the environment, it just does different chemistry. You put it back in this environment, it does the chemistry again that environment favors. So it's not evolvable. Positive feedback loops can amplify flux, can make it more complex, but it can't change it into something that it wasn't before.
Right.
As soon as you've got genes, then you begin to have kind of control systems that are capable of you move to a different environment and now you shut down this system so that doesn't happen, and now you're responding to your environment, and you might wait out until the conditions change again and then you switch them back on again. As soon as you've got genes, you're capable of doing something different in response to your environment. And as soon as you've got that, you're dealing with something that amounts to some form of agency, whether you want to call it agency or not. You're responding to your environment as an entity. Now, how do you respond? Well, that requires, at the very least, proteins, molecular machines, things that are capable of doing things, of changing their conformation in some way so that you will allow a proton through or not allow a proton through, or whatever it may be. But when we get to the ribosome, protein building factories, they are amazing things, and we're still away from explaining how you start with the simplest bits of RNA and bits of amino acids and so on, and how you assemble them into something which is this molecular machine that it's called processing along the RNA, but effectively it's moving. It's a giant molecular machine that moves down and makes proteins. How do you get going with that? They're deep, difficult questions, and the first step is to have ideas as to how it might happen, and then the second step is to test those ideas. And frankly, from my own point of view, we have very limited ideas on how that gets going. We have some, but they're not very good. But by the time you've got to a world where you've got DNA, RNA, and proteins inside cells, then I think we have a world where you're going to have something that looks like agency, where cells will behave in a certain way as an entity by having molecular machines, proteins that are capable of responding to the environment in one way or another. And I think as soon as you've got proteins, well, it's not too difficult. I mean, a lot of people worry about the sequence space involved in proteins, but it's not such a difficult problem because they will tend to fold into specific shapes and folds, and very often will bind to things. So bind to metal ions or bind to cofactors. And that forces a certain shape onto you anyway. And so you're fishing out of this almost infinite number of possible protein shapes, a certain number that have function from the very beginning and which selection can act on. So if you've already got a metabolism which is spontaneously happening, positive feedback loops which are effectively catalyzed by cofactors, so simple things as simple as metal ions sometimes, or more complex things like nucleotide cofactors. So things like ATP, quite a complex molecule, but a product of metabolism. As soon as you've got those things feeding back, then the next step is, okay, so the protein binds to these things and improves their function, or it could make their function worse. If it makes their function worse and it's part of a cell that doesn't work, then that's going to be outcompeted by natural selection. As you know, in this cell, which happens to have a protein which folded correctly, that one goes on and makes copies of itself. So what
makes complete sense.
It's not hard to get to protein structures, not hard to get to the correct protein structures, not hard to have selection that operates on those protein structures. But how you get that very first bit to a ribosome that recognizes that here is the start codon for making this protein, and now I'm going to move along this RNA one step at a time, and I'm going to bring in these transfer RNAs, join them together, turn it into a peptide, and shuffle along a little bit more. That does my head in.
Yeah.
It's got to be explicable. I'm sure it's explicable, but it's almost a statement of faith that I'm sure that that's explicable. And I hope that we can answer it in the coming years. And it's one of the reasons I get out of bed in the morning. They're just such exciting problems to work on.
Right. I'll add a few animations of proteins at work just on the screen because I think they're some of the coolest things in the world. I think seeing it for the first time was one of those just eye-opening, reality-shattering moments of like, oh, I need to dedicate my whole life to learning about these things and telling them to people. Like it gave me goosebumps on every square inch of my skin. It was like, this is crazy. Like, are you telling me that the human body is powered by billions of tiny molecular machines and somehow it's all working together? It's not like my right arm never gains autonomy from the rest of the body and just acts in unit. Like, how has that happened? Do we know at all? Can we date proteins at all? Do we know in any way what were the first proteins that were made and what were the newer sort of inventions? Is there a way that we can date proteins?
Yes. I mean, date in terms of directly dating by finding this protein in a rock which is known to be 4 billion years old, the answer is no, we can't do that. In terms of a genetic tree, because genes code for proteins, so you can build a tree of genes, all genomes now, and then we can't be certain that it's true because the longer we go back, further back into the past we go, the more uncertainty there is. Genes get passed around by what's called lateral gene transfer. This bacteria picks up a bit of DNA from the environment that came from something completely unrelated and incorporates it into its own genome. This kind of thing happens all the time, and over billions of years it can really confound the picture. But with a lot of patients, I don't do this kind of work, but phylogeneticists with huge computational power have pieced together a tree of life that goes right back to what's called Luca, the last universal common ancestor. And there's a lot of uncertainty. Different people will come up with anything between about 300 or 3,000 genes, and therefore coding for 300 up to 3,000 proteins. So there's a huge amount of uncertainty, but there's always the same core in there. And some of the deepest core is the genes involved in making proteins. And you start with DNA, you transcribe it into RNA, the kind of the bit which is the little string which is coding for a specific protein. and then you use the ribosome to translate that into the protein itself. So this is what's been known as the central dogma, this idea that DNA makes RNA, makes proteins. And the earliest proteins are the ones that are doing that kind of thing.
Makes sense.
There are, equally old proteins involved in metabolism in one way or another. Things like the ATP synthase, which is an amazing rotating motor protein that sits in the membrane and is powered to spin by protons coming through it. It's ancient. It seems also to go all the way back to Luca, but in some sense you have to be able to rationalize the relative timing, which is to say the ATP synthase is a molecular machine which undoubtedly is coded by genes and with a degree of sophistication which is not this is coded by proper genes, which we're using a ribosome already. You've got a full genetic code before you have an ATP synthase. So you must have had a ribosome before you had an ATP synthase in that sense, because you need to have a fully implemented genetic code. So you can, although that's not a proof that the ribosome came before the ATP synthase, it's kind of just logical. They may have been very similar in time, but the ribosome has to be among the most ancient machines out there. And it's also one of the most complex and stunning machines out there. It's still this big kind of questions about how these things came to be.
Yeah. You have another great quote, which says, "In my book, the ATP synthase should be as symbolic of life as the double helix of DNA. Now that you mention it, this is my book, and it is." I really liked that quote.
I've forgotten that.
For people that haven't heard of ATP synthase before, describe its importance in life.
So ATP, I don't know how many people are familiar with ATP. It's taught in schools and so on. It's usually just described as the universal energy currency, and it's a molecule with a tail of 3 phosphate groups, which are kind of an odd way of going about things, but that's how it works across all of biology. And if you want to make DNA, or you want to make RNA, or you want to make proteins, all of them are using ATP to do it. And all of them have this tail of the 3 phosphates. So it's a really interesting question. How do you get there? Now, the ATP synthase is basically adding that tail, or at least adding the last bit of the tail. So it's converting ADP, which is the diphosphate, into ATP, which is the triphosphate. So you're adding 1 phosphate onto that tail, and it's doing it. I say it's a rotating motor. It sits in the membrane. The membrane's got a charge across it, and the charge is really produced by pumping protons. So this is the nucleus of a hydrogen ion across the membrane. So on one side, you've got a reservoir of protons. You think of it almost like a hydroelectric power scheme with the reservoir on one side. The membrane is like the dam. And the ATP synthase is like the electrical turbine. And as the protons are flowing, like water would flow through the turbine, you're powering its rotation. And that's causing a mechanical change in the protein. And the mechanical change is adding that phosphate group on to make ATP from ADP. So it's a kind of a crazy device. It's stunning. It spins at about 500 rotations per second, up to about 500. And it's exquisitely organized. The speed at which it rotates depends on the electrical potential across the membrane. So there's people have spent their whole careers working on how this thing works. And so it's really symbolic of not of the informational side of biology, but of the functional side of biology. How do cells make a living in the world? And yes, you need genes to do that, but cells are entities that have a lot of moving parts. And those moving parts are what powers all the work that enables a cell to make a copy of itself. And the ATP synthase is possibly the most symbolic protein that's really driving all of the energetics of a cell into powering growth and reproduction and copying of DNA and RNA. All the work that a cell is doing is pretty much powered by that astonishing molecule. And one of the questions for the origin of life is, well, how do you get to that point?
Yes.
There must have been ways before you have this complex molecule of driving ATP synthesis. And one of the nice things about a hydrothermal vent is you've got the structure, you've got the cell-like structures, you've got acidic oceans full of protons, you've got alkaline fluids in the vents. And so you've got a natural gradient. You didn't have to pump protons out. They're out anyway, and they can come in and drive work. And the work doesn't have to be an exquisite rotating motor. That work, actually, the earliest work, I think, was making CO2 and hydrogen more reactive so that they will break down those kinetic barriers to their reaction and react to form organic molecules. So the original work that the proton gradients were doing was nothing to do with ATP. It was all to do with making more of yourself, making more organic molecules. And you kind of build up from there. By the time you got to selection, now you can add an ATP synthase. Now you've got a system which is capable of honing an exquisite molecule like that.
Is it fair to say that the geochemical environment is what was able to stabilize all of the intermediates in the biochemistry? So the biochemistry one of the problems with evolution is that you have all of these intermediate states that need to be stable on their own before you get to the magnificent endpoint, right? But the fact that this biochemical system was able to lean on the geochemistry components, it was able to kind of build it step by step and then slowly become less reliant on the geochemistry as it built component by component. And the geochemistry of the whole thing made everything stable step by step. It was always a more stable configuration over time.
That's pretty much it in a nutshell, yes. I think it's not necessarily stability so much as replenishment, it's turnover. I mean, one way I've thought about a hydrothermal system is we tend to see ourselves as physical beings. And it slightly masks the idea that, well, if you put a plastic bag over your head, you'll be dead in about a minute and a half. So why? Well, because we are inside all of our cells, we are respiring, and that respiration is providing the energy that keeps us alive. So where in our cells? Well, it's the mitochondria. It's this ATP synthase that we've just been talking about. That is driving all the work. How is that powered? Well, that is powered by effectively breaking down food, bringing it into the mitochondria, these powerhouses in our cells that were bacteria once, and effectively stripping out the electrons and the protons from those molecules. You have then a current of electrons flowing to oxygen, so we have to have a cardiovascular system which is bringing in oxygen in the lungs, into the blood vessels, and then delivering it to all the cells and into the mitochondria. So now we've got at one end the electrons, at the other end the electron acceptor, which is oxygen. Current of electrons, that current of electrons is powering the extrusion of protons across the membrane. So now we have a charge on the membrane because protons have a positive charge. That charge is in the order of it's about 180 to 200 millivolts, but the membrane is very, very thin. It's about 5 millionths of a millimeter thick. So if you were to shrink yourself down to the size of a molecule and stand next to that membrane, the field strength that you would experience, the force field that you would experience, is about 30 million volts per meter, which is the same as a bolt of lightning. So you've got this huge force field across this membrane, and it's that that's driving the spinning of the ATP synthase. It's that that's driving the production of ATP and all the energy that's going on in the cell. So we are big physical beings, but get right down inside the cells, and we have this continuous flow, the continual delivery of electrons to the mitochondria, the continual transfer of them onto oxygen, the continual pumping of protons. And the reason, if you put a plastic bag over your head, that you die is you're no longer able to deliver the oxygen or the substrates to the mitochondria. So we are a continuous chemical reaction.
Yes.
And if you think about a primordial soup in relation to that, well, what is the continual chemical reaction there? There isn't really one in a comparable sense. If you think about a hydrothermal vent, you've got a continual flow. It's like having a kind of geological cardiovascular system that's continually providing you with the electrons that you need to react with in the case of a vent, CO2 rather than O2, to make organic molecules. So you've got this system which is capable of continual replenishment of what you need to be living. So it's not really stability so much as continuity.
Right.
This kind of the driving forces that are going to keep on making things, keep on growing, keep on driving growth. Where does this, if you're thinking about why does one cell want to become two cells, which is a famous question, and why would things grow at all? Where does that impetus come from? It simply comes from the Earth being a giant battery with all the electrons down there coming out, driving this reaction. It's doubling is almost inevitable in a hydrothermal system. Growth is just an outcome of these two phases that are constantly reacting with each other.
I think you just cleared up a very big misconception that I had as well. You said that ATP synthase dates basically all the way back to Luca. For some reason in my head, I had ATP synthase evolving around the same time as mitochondria and the Great Leap.
No, it goes way back before mitochondria.
Right.
Yes.
I had never separated the two in my head. For some reason, I had always assumed that during that Great Leap, and we can kind of jump to that now, I think we can leap to that point now, I always assumed that ATP synthase evolved then because you needed the mitochondrial pump, that artificial proton gradient. But you're saying that gradient comes from the hydrothermal events. Therefore, ATP synthase definitely massively predates it by billions of years, not just a little bit.
Yeah, I mean, bacteria, so mitochondria were bacteria once, and they brought with them all of the machinery for respiration, including the ATP synthase. And all archaea pretty much have exactly the same kit. It's a little bit different. If you look at the structure of the ATP synthase in archaea compared to bacteria, there are some obvious differences, but still, it's a rotating motor with the same components.
Right.
It works in the same way to do the same job. And there's no question that the common ancestor of those two things had a motor that was doing that. And it is the most exquisite molecular machine, right up there with the ribosome, and almost as ancient as the ribosome. But logically, the machine that makes the proteins that can be selected has to come before the ATP, which is one of the machines which is being selected.
Incredible. That's a very big thing that you've helped to clarify for me. Let's talk about that. So we have an ATP synthase, we have metabolism that's creating organic matter, we have a scaffolding. At what point do we become the first bacteria? We're replicating cells. When does that system become bacteria for the first time?
Again, there's no agreement about this kind of
Yes.
thing. In my book, and I get this idea more or less from Bill Martin, that the common ancestor Luca lived in deep sea hydrothermal vents, was not really a free living organism. I should say Bill Martin and Mike Russell had some great papers on this 20 years ago. And they got a kind of caged Luca that lived in these vents. And then bacteria and archaea, which look a lot like bacteria, but they're quite different in their genetics and some of their biochemistry, they emerged separately from a common ancestor in a vent. And when I first heard that idea, I was kind of outraged by it, really. It sounds really literally outrageous. But it's very, very difficult to explain the observation that bacteria and archaea are in some respects clearly related. They have the same genetic code, they have the same DNA, the same RNA, the same ribosomes, the same kind of core structure, but their membranes are different in their chemistry. The cell walls are different. The replication machinery of DNA is different. A lot of the enzymes involved in metabolism is different. And so they're kind of clearly related, but at the same time, they don't appear to be very closely related. And so what kind of a cell was the common ancestor if they've got different membranes? What kind of membrane did the common ancestor have then?
Right.
And their original idea is, well, they didn't have a membrane at all. I don't really agree with that anymore, though I found it a thrilling idea at the time. I would now say it had a membrane, really a fatty acid bilayer, a very simple membrane. Why do I think it needed a simple membrane? Because if it had a complex modern membrane, stuff can't get in and out.
Yeah.
If it's got a kind of crappy membrane, then protons especially can come in and they can leave again. And so you've got a system which is partly open. Stuff comes in and leaves again passively. You don't need a pump for that system to work. So you were asking about the stability of a hydrothermal vent. Well, if you've got crappy membranes, then stuff can flow through them. You're not going to wash away proteins. You're not going to wash away things like ATP or even sugars, but you will wash away protons and metal ions and things like that. So you're continually replenishing and dissipating the stuff that needs to be replenished and dissipated, and you're retaining the things that you need to retain. And this is so this is not a free living cell. This is a cell that's the common ancestor of bacteria and archaea living in hydrothermal vents. Population of them. It's not a single cell. Population spreading through these vents. And when do they leave? Well, the only time they can leave is when they've figured out how to make the pumps and effectively leave this system, which is providing you with everything you need, go into the open oceans or into the deep hot biosphere or wherever you may have gone, and do all of this stuff for yourself.
Right.
You need to be able to find this hydrogen molecule, take the electrons from it, pass it on to CO2 or maybe onto ferric iron, rusty iron, or whatever it may be, and use that to pump protons or sodium ions across the membrane and use those to drive your ATP synthase. So now you've got a complete circuit. It's a level of sophistication which is way up on what you were doing in a vent. Now you've got proton-type membranes and molecular machines that will pump things. This is where the bacteria and the archaea really differ. They invented all of that themselves. This is why I do agree that they emerged separately from a common ancestor that was basically living in the vents. So when did bacteria appear? 4 billion years ago, a long time ago. Archaea about the same time, from a common ancestor that I don't think was entirely free living. I think it was living in these deep sea hydrothermal systems and utterly dependent on those systems for its existence. And as soon as you've figured out how do I pump and how do I improve my membranes, then within the space of possibly a few generations, the bacteria and the archaea emerge independently. It doesn't. Once you've got a selection that works, things don't have to take long. There's a kind of an assumption that because life is 4 billion years old, and because you see long periods of stasis of hundreds of millions of years where nothing much seems to happen, that selection is therefore slow or laborious and takes a long time. But then you see periods of very abrupt change, which freaks everybody out, like the Cambrian explosion or the origin of the eukaryotic cell, where suddenly everything changed. And ideas of abrupt change, Stephen Jay Gould spent a lot of time talking about that kind of thing. Punctuated equilibrium was what he called it. But the idea that you can have very rapid change if the conditions change, it's quite an old one. And I think there's a lot of truth. Life will tend to stabilize in certain states. And if the conditions don't change much, it'll stay in that state indefinitely for, literally billions of years. But when things are changing, think generations. And if you're thinking generations in bacteria, a generation can be half an hour. If you were more conservative and give it a day, in the space of 1 million generations, that's a huge amount of change you could have had if the conditions are driving it. 1 million generations is only 1 million years. It doesn't require hundreds of millions of years. How long did the origin of life take? Did it have to be tens or hundreds of millions of years? Why not say 1,000 years? We don't really have a handle on how long it has to take.
So why do you think it took 2 billion years for that leap to happen? I presume so there was a phagocytotic event. One bacteria ate the archaea, internalized that mitochondria, somehow figured out a way of stripping away the non-core components, and then it has a battery pack. Is that roughly what happened?
So this is what I would call the origin of the eukaryotic cell that you're referring to here. So our own cells and plant cells and algae and fungi and so on, we all have this one cell type called the eukaryotic cell. And eukaryotic just means true nucleus. So we have our DNA packaged up in a nucleus, which is a kind of, you can think of it as a control center inside the cell where the genetic information is. Our cells are much bigger than bacterial cells, and they've got all kinds of compartments, including the mitochondria, which were incorporated as from bacteria and became an endosymbiont, so a bacterium living inside another cell and linked very closely with how it made its living. and eventually becomes what we call an organelle, so basically an integrated component of a cell as we know it, barely recognizable as a bacterium. And not really a bacterium at all anymore, but with a, if you look at it genetically or in terms of its function, you realize that it is derived very directly from bacteria. So the puzzle then is that just happened once. So all eukaryotic cells have the same cell structure. And you see whole textbooks that go through, the endoplasmic reticulum, the Golgi apparatus, the lysosomes, the microtubules, all the rest of it. All eukaryotes have all of those things, and bacteria and archaea, they have bits and pieces, but basically none of those things. And so, how do you explain that? It seems very odd. It's the biggest discontinuity in all of biology between prokaryotes, which don't have a nucleus, and eukaryotes, which have all of this complexity, and all share all of that complexity. And the first thing I'd say is, it's not about exploring genetic sequence space. It's not as if bacteria have their set of genes, they mutate, they change, they have offspring, they live in different environments. They effectively, their genes are continually changing and coming up with solutions to problems, and that's called the sequence space. This is all of the possible proteins that you could have encoded by all the genes that you could have. If there's one magic combination that says, aha, now with this combination, I can go on and become complex. Well, it should have happened multiple times in bacteria and archaea, but we don't see that. They all remain in their morphology quite simple. In their biochemistry, in their genetics, in their molecular machines, they're really complex, but in their morphology, they're 10,000 times smaller than a eukaryotic cell and have none of these internal compartments. So how did eukaryotes do it? Well, I think there's a very strong argument to say that it was that one of these relatively simple archaeal cells, and now we would say it's a particular group called the Asgards. The Asgard archaea was the host cell that acquired a bacterial endosymbiont that went on to become the mitochondria. And now we're dealing with first of all, a very different dynamic. It's not easy for bacteria or archaea, for prokaryotes, to get a cell living inside them. They're not generally phagocytes. They don't go around eating other cells for a living. Occasionally they do, but mostly they don't.
Okay.
So it's not easy to get in. And once you've got in, mostly it'll go wrong pretty quickly. You either get digested or you just fail to replicate or whatever it may be. So why do all eukaryotes have all of these things in common? It's not because they have adapted to a common way of life. An algal cell floating in the ocean has the same machinery at a cellular level as one of your kidney cells. It's still got the endoplasmic reticulum. It's still got the nucleus. It's still the nuclear pore. It's all that machinery.
That's such a cool sentence. That's such a cool sentence. Yeah, it's really worth restating how cool that is.
Yeah. So, but it's not about its lifestyle.
Yes.
Your kidney cell and that algal cell in the ocean have got completely different lifestyles. One's photosynthetic, one's doing a particular job, but they've got all the same machinery inside them. Why did it evolve? It's not about adaptation to an external environment or a way of life. It can't possibly be. So, but there is a reasonable thing. It's about having you're a small, simple cell. You get an endosymbiont that it will eat you if it has half a chance. But it's also providing you with a service. You've got a kind of a strained relationship with something inside you, which is potentially going to cause you real harm, but also can give you real benefits. And so you've got this long internal relationship with your own, what become the mitochondria. They lose most of their genes. They become effectively adapted to provide the host cell with a service. And part of that is huge amounts of energy in relation to anything that their forebears used to have. And that energy allows you to have more genes, and having more genes allows you to do more experimentation and to have more proteins and to become larger. And also, you need different selection pressures. You've got these cells living inside you that may eat you if you don't provide them with food. So if you're going to provide them with food, then you better have a transport network. Any kind of transport network is better than no transport network. Bring stuff in from the outside, feed your ravenous monsters inside, your endosymbionts inside. And the better you can do that, the better you'll do. Being bigger and having more genes and having a transport network and having a dynamic cytoskeleton and motor proteins and all the rest of it, you feed your endosymbionts that way and you will thrive that way. So there's a driving force towards greater complexity just by having cells living inside. Where did they live in the ocean? How did they live? I don't know. They were almost certainly eating. They were heterotrophic. They were taking organic molecules from outside. Were they like a fungus? Maybe. Were they phagocytes? Maybe. But they're taking stuff from the outside. They're feeding their endosymbionts. They're getting stuff back from their endosymbionts, and they're living as single-celled critters in the oceans. One of them eats a cyanobacterium at some point, incorporates in a similar process, which becomes a chloroplast. Now you have your single-celled alga. The other guy that didn't get the chloroplast eventually ends up with one of your kidney cells. But that was a turning point.
Yeah. I'm not sure I understand from that how we know for sure it only happened once. What did this involution of the cells and how do we know that happened only one time?
Well, we don't know it only happened one time, but we don't have any evidence that it happened more than once.
Okay.
So if you look at all eukaryotes, so all plants and animals and algae and fungi and all the rest of it, we share all of these things. We obviously have a common ancestor. And that common ancestor, by definition, arose once. That never means a single mad cell. It means a population of things, and the ancestors of that, the descendants of that population diversify into plants and animals and whatever else. But because we share all of this stuff, we can impute that population of cells in the common ancestor already had all of those things. It had an endoplasmic reticulum, it had a nucleus, it did do sex, it did, it had got all of this kit.
Yes.
And then you say, okay, so how did all this kit evolve? And the answer is, well, we don't really know, or at least we can't agree, because the outgroups, the things that you'd say, okay, well, let's compare it with something else. Well, they're the bacteria and the archaea, and they don't look very similar at all. They don't have any of this kit. So there's a long gap between the kind of morphological complexity of bacteria and archaea and the morphological complexity of all eukaryotes.
Right.
And from that, we can say all eukaryotes arose. They share a common ancestor, which by definition arose once. Eukaryotes are monophyletic. And we know enough that the ancestor was an archaeal host cell with a bacterial endosymbiont that went on to become the mitochondria. So the ancestor was something like that. Now, this could have happened, or some similar things could have happened on thousands of occasions.
Right.
But there's no evidence that it did. So if it did, then they all fell extinct. Now, how would we discover something? Well, first of all, you can go sampling. You look in all kinds of environments. Look up in the stratosphere, look down in the deepest mines, go to the deep hot biosphere, sample from the deep oceans. We've been doing all of this kind of thing for decades. Have we ever found anything that didn't fall into these three groups of bacteria, archaea, and eukaryotes? The answer is no, we never have. There are some things which are a bit equivocal. We don't quite know what they are, but they're very, very uncommon. And we've never found a second one of them. So it's difficult to place what they are.
That is a puzzling point. I'd never thought about it, that there hasn't been anything that's been discovered ever, or remnants of anything that doesn't fit into sort of three niche categories. That's pretty weird. We
found whole groups of bacteria and whole groups of archaea, which are kind of highly derived, I would say. I mean, they look like they're very, very small cells. They're symbionts. They're snuggling up alongside each other. They've lost a lot of the kit that they need to live as independent cells. So if you sequence them, what you see is half a cell almost, a tiny thing that can't live by itself, and they've become very, very highly derived, and they take up a pretty unique position in the tree of life. But they're still clearly bacteria or archaea, and we don't see eukaryotes really very similar to that. The other thing you can do is look in the fossil record and go back. And so a lot of people will think of the Cambrian explosion when we first see animals in the fossil record. as being the beginning of the fossil record, but it's not. You go back before and we see what are called the ediacaran fauna. So these are quite large sessile filter feeders, things that functionally today are a bit like corals and sponges, but they look a bit like plants. They've got fronds and things. We see those 20, 30 million years before the Cambrian explosion, or before the Cambrian period. But way before that, we see fossil bacteria and fossil eukaryotic cells, and there's things. There's algal cells, Bangiomorpha, found 1 billion years ago in the fossil record. So cells will fossilize, bacteria will fossilize, and so then the question is, okay, so do we see then in the fossil record multiple origins of what looks like complex life, or can we consign these things to modern groups? And there the answer is a bit more ambiguous, but it's certainly not clear that there were multiple attempts, if you like, at coming up with complex life. Pretty much everything that we've seen looks like it, in one way or another, fits in with the modern groups that we know about. So geologists might argue about that, and various things are discovered every now and then that looks like maybe something complex, and then the general interpretation is no, it was just a conglomeration of kind of crap that got squashed together and is not actually a functional organism. It's just a conglomeration. Is that real? Is that the correct interpretation, or is it in fact a really complex cell that we just don't know anything about it?
Right.
You take the pick, but the simplest interpretation is that it's not. We don't really have any good evidence for multiple origins of complex life. And so we fall back on the observation that it happened once with a certain question mark about it.
Right, that it could be a survivorship bias. It seems unlikely to me that there wouldn't be countless organisms lost to history, right? Lost to entropy, completely destroyed. Maybe some technology is required. Some high tech technology is required to unearth clues at the bed of the sea, where maybe there are countless organisms that we're completely missing now. But it seems impossible that there wouldn't be entire trains of evolutionary development that would just go dead and we wouldn't ever know about it because there wouldn't be evidence for it, right? It seems unlikely.
I think that it wouldn't surprise me very much if we found very rarely and very occasionally groups that appear to be not fitting into modern groups of bacteria, archaea, and eukaryotes.
Right.
Maybe it would be a separate origin of potentially complex life, but did it work? Is it working? Do they have a high enough population density? There's all kinds of reasons it can be thrown up and then go wrong and disappear without trace, really. And that's the most likely answer in my mind, is that it's not a singularity that can only happen once. It's something that can have happened on thousands or millions of occasions, but the chances of it working out in the end are quite small. And the only example we see where it really did work out, the evolutionary distance traveled from the known ancestors, which are roughly known bacteria, roughly known archaea, and the common ancestor of all eukaryotes, is such a long evolutionary distance that it has to say that was hard. That's a long way. That's not a trivial distance that they had to cover to come up with a cell that was basically stable, that was able to radiate to occupy all these different niches. So just again, from the shape of the tree of life, I would say that was not easy.
Right. What do we know about how we go from that bacteria? Okay, it has its power pack. It can now leave the hydrothermal vents because it's graduated from nursery. It's fully able to survive on its own. How do we get those primitive nervous systems, those first neurons that are electrically excitable, the first sensory systems? What do we know about how those things come into the picture?
Well, I'm that's not what I really work on, but I do have some thoughts. I mean, the first thing I would say is that a neuron is not so very different to other types of cell. Now, the first thing to say is we're talking about eukaryotic cells here. We're talking about animals with nervous systems and neurons in nervous systems. And what they're doing, in my mind, and this is a gross simplification, but what they're doing is passing signals on by depolarizing. they're excitable. They have a charge across their plasma membrane, and that can depolarize and pass on a signal saying something or other. Now, all cells have a charge across their plasma membrane, and so all cells are neuron-like in that way, and bacterial cells are as well in the same way. So all cells have got a charge across the membrane, and what's then interesting and slightly different about neurons is they will dynamically change the charge. They will depolarize, do something, repolarize, and do that repeatedly, and they kind of their life is continually depolarizing and repolarizing again. Whereas for most cells, they're just polarized and they stay that way. And if they depolarize, they'll get ejected, they'll die, they'll be, but the amount of invention that's required to go from a cell with a charge on the membrane to a cell with a charge on the membrane, which is capable of deflating and then reflating, it's not such a long way to go in terms of evolutionary distance. And in terms of how, let's say, bacteria work, I mean, one of the more beautiful examples that I'm familiar with is if a bacterium is attacked by viruses, what we call bacteriophages, one of two things can happen, I suppose. Either they're going to get taken out by the virus, or if it's kind of inevitable that the virus is going to come in, either the virus is going to make copies of itself, exploit that bacterial cell, and then invade the next bacterial cell, and so on, or the bacterial cell can prevent that from happening by killing itself, by a form of controlled cell death. Now, how does it do that? Well, it does that by depolarizing its membrane, as terminal depolarization of the membrane. So if it gets invaded by viruses, it depolarizes itself and kills itself before the virus has a chance to replicate itself and infect the next cell. And this is quite well known. This happens a lot, especially in marine blooms of cyanobacteria, say, these kind of things. All kinds of algal blooms will do the same thing. And it's quite easy to show in terms of known evolutionary processes like kin selection, that it is to the advantage of this bacterial cell to kill itself so that the closely related genes in the neighboring bacteria, the related bacteria, are going to do better.
Right.
So in terms of the selfish gene kind of ideas, all of that makes perfect sense. What's interesting to me, though, is it's about the depolarization of the cell as an entity. And there's all kinds of, these are things that I've kind of worried about. How does a cell know how it's doing? How does it know that it was just invaded by a virus? How does it distinguish between that and being a little bit too hot or a bit too cold or not having enough oxygen or having a toxin there? How does a cell which doesn't have a nervous system, doesn't have any eyes or nose or anything, somehow it's got to understand enough about the environment? Things happen in the environment. That perturbs its metabolism, because there's nothing else in there beyond metabolism. And gene expression in that sense is a response to perturbation of metabolism. How does it know what it should do? And there may be multiple conflicting things, and you can imagine a lot of this is going to be positive feedback loops or negative feedback loops, or it's just automated, you might say. But you can have conflict between these different systems. How do you make a decision as to which one you're going to do? I think that the membrane potential itself, which is effectively generated by metabolism and powers metabolism in this odd closed loop, is going to tell you a lot about how you're doing in relation to the environment as a bacterial cell.
Right.
And now you incorporate this bacterial cell inside an archaeon, and eventually becomes a eukaryotic cell with mitochondria. And the control of cell death is still controlled by the mitochondria, which will depolarize if things are going wrong and kill the whole entity. And then you have a multicellular organism, and the pathways of development are a lot about the electrical potential across the plasma membrane. You can have voltage maps across the development of small organisms, things like planaria, some of Mike Levin's work, for example.
Yes. The
head or the tail and so on are effectively defined by the voltage across networks of cells that share a common voltage connected by gap junctions. So all of this is kind of electrical. It's all working on an electrical basis, and inside it all, we've got the mitochondria, which have got their own voltage, and which are somehow talking to all the rest of this network in ways that we don't really know how that works. And we still see apoptosis, these forms of controlled cell death, which still depend on the membrane potential. And an outcome of all of this, how do you know how you're doing in relation to the environment? A lot depends on the electrical charges. They will be modulated according to exactly how metabolism is doing in relation to the environment. As you get more sophisticated, you end up with a subpopulation of cells that become neurons, which are doing this actively. They're effectively sampling from the rest of the body and firing by exactly the same processes of depolarization of the membrane potential to instruct your behavior in relation to the environment. So, it's a very broad brushstroke picture, but neurons in that context are doing the same things that bacterial cells always did, using the same machinery, just in a more sophisticated way.
Right. Very cool. Very, very well explained. I get the sense that you think electricity and bioelectricity might be the key to some of biology's largest mysteries at the moment, and it's been relatively unexplored, and there's not been enough research done in those areas. Would that be correct to say?
Absolutely, yeah. I mean, it's an area which I think a lot of people see as crank science, to be honest. And there've been, people like Mike Levin have been doing really good work. Still, there's a fair amount of suspicion from let's say, more mainstream scientists about it. But every time there's the very name molecular biology effectively has the answer in its title. It says everything's about molecules and chemistry.
Right.
Now, if you take a step back and you think, how do we know how mitochondria work? Well, it goes back to Peter Mitchell and Jennifer Moyle back in the 1960s, showing that it's part of a bigger system. It's not a property of this molecule or that molecule or any one protein. It requires the system. It requires the membrane. It requires the pumps in the membrane. It requires orientation. It requires spatial direction. You're pumping in a certain direction. They're coming back in a different direction. So the way that respiration works is a property of a larger system, and you end up with an electrical charge across that membrane. And that membrane in a bacterial cell is the bounding membrane between the inside of the cell and the outside world. And in a mitochondria, in some sense, it still is. Even though it's buried inside a cell, we're delivering all this oxygen and all this food and electrons straight to this place. If there's anything that changes in the environment, you put a plastic bag over your head. The place where it's felt first is in your mitochondria, which now don't have enough oxygen. So you can't respire anymore. You're not passing electrons on anymore, and metabolism doesn't work properly anymore. So the place where you feel that plastic bag first, if you like, is in your mitochondria.
Right.
So that is still, even though it seems to be buried inside us, it's still the interface with the outside world. So all of this is electrical. It's part of a bigger system. So the idea then that this bigger system also applies to networks of cells, and that how they are kind of predetermined that this is going to become the head and this is going to become the tail. The idea that electrical charge is part of that, I find very appealing. A lot of people it's not the right explanatory paradigm for them, because they think in terms of the nuts and bolts of proteins rather than the system. And again, when you get up to whole central nervous systems, when you're thinking about voltage maps anyway as defining how the entity is working as an agent in the world, as an individual, then the central nervous system or nervous system is kind of built up on this platform of electrical charges and changes in charges as being the language that's explaining how you're doing in relation to the world. There's all kinds of things that is partly voltage. There's potentially other kinds of field involved in there, and lots of people get very worried as soon as anybody uses the word electromagnetic field in biology. Most molecular biologists will start backing away.
Right.
And in some sense, they may be right, because there is a lot of kind of, I wouldn't like to say pseudoscience, but a lot of science is difficult to judge whether it was good science or not.
Yes.
And there's also a lot of vested interest that if it turns out that all kinds of electrical devices do in fact influence our physiology in some way. Well, do we want to know? Probably we should know. Do people want us to know? I mean, you can very easily end up in a kind of conspiracy theory land.
Yes.
So it's a place that most people are very cautious about going anywhere near. I think, from my own point of view, the idea that charge and fields and voltage maps and ways of understanding how you're doing in relation to the world, how can metabolism, which is even in a bacterial cell, 1 billion reactions every second, second after second, how does all that mess, all of that chemistry, how do you kind of integrate it and come up with an answer like that just says, okay, I'm doing bad, go?
Yes.
I think that's what the chargers are doing. That's what it is integrating the system as a whole and giving you a snapshot, kind of finger to the wind answer as to how you're doing.
It's so phenomenal. People are going to clip what you said there and use it as proof of the Gonsfeld experiment in like the 1930s, where telepathy was supposedly proven, communicating information via just thinking about it. But that was phenomenally cool and well explained. How do you think it fits into the picture of consciousness? First off, we spent a long time in this conversation going through the timeline of evolution. Are you in the field? Are you in the camp of, at some point in this development, there was a time when you didn't have consciousness and then you did?
I would say a couple of things. I mean, the first thing to say is I'm not a neurologist, and I don't work on consciousness in a kind of very systematic way.
Yes.
But it's just one of those questions that's too interesting to not be interested in.
Exactly.
And also, in recent years, I've found myself working a little bit on anesthetics, mostly through a guy called Luca Turin, who turned up and told me they work on mitochondria. I didn't know that. It's not a position that everybody agrees about, but it looks more and more likely that they really are influencing mitochondria and potentially the membrane potential in electrical fields and so on. So that's been an interesting way in to the question for me. But there's a kind of step back a bit, and there's this bigger question. Okay, so let's say it's true. Anesthetics interfere with mitochondria. Why? Why would that undermine consciousness? Is it just that you don't have enough ATP anymore? You have a kind of synaptic power failure, and that's the only reason? Or is there something more fundamental and interesting about it? And when you take a step back and think, well, the mitochondria were bacteria once, and the membrane which has got the charge on it is the membrane that was the interface between the inside world and the outside world. And if a bacterial cell wants to know how it's doing, it's somehow got to integrate all of this chemistry, this billion reactions a second, into a single readout, and that readout can be the membrane potential. That's telling you something about how you're doing in relation to the world, and that's what you're playing with an anesthetic in relation to the mitochondria. So there's an interesting way into the question, and from my point of view, I have nothing to add about neural networks or computation or any of those standard neurology questions. I can never remember the structure of the brain and all of these different regions. It does my head in. But it struck me for a long time that the depolarization of a neuron giving rise to feelings of things. So the hard problem, it's usually called the idea of qualia, of feelings, of that we feel something. Why would potassium ions or sodium ions or calcium ions coming into a cell give rise to a feeling of anything at all? What is a feeling in physical terms? And again, I think a lot of people back away as soon as you start asking those questions because it feels like it's not really science.
Yes.
But at the same time, I think most biologists would agree that the feelings are real, which is to say they're not a complete fabrication. They're something that we can see in animals. We can see in ourselves. We can tell. We understand our own emotions from within. So I think most people would agree that they're real. And if they're real, I think most people would agree again that they evolved by natural selection. We primarily have feelings about ourselves in relation to the environment. are we good or are we bad, or how are we doing here? We're not primarily conscious of the movements of the stars or the heavens or of celestial beings, or we're conscious that we've got tummy ache or whatever it might be. It's very physical, and it's very much about organism in an environment. So it's about the organisms. It evolved by selection. I don't think many biologists would disagree with that. They're real and therefore physical. And if they're physical, we should be able to measure them. And if we can't measure them, then we have a problem. And I don't think that there's anything that we know about neural nets or the function of the mind that explains why this pattern of neural firing is associated with conscious awareness, and this very similar pattern of neural firing is unconscious or subconscious or whatever it may be.
Yes.
It seems to be the wrong level of analysis. We don't seem to be able to distinguish between different types of network at the network level. And when I come back to thinking about bacterial cells, which I'm far more comfortable with now, and I think, okay, I've got a cell, it's an oblong, it's got metabolism in it. Outside, we've got an environment. The environment is harsh in this way. It perturbs metabolism in that way. Metabolism is now not generating a membrane potential in the same way, and that's giving me a kind of an integrated feedback on my position in relation to the world. Is that what a feeling is?
Yeah.
In physical terms, is it something to do with the electrical charges on the membrane being modulated, possibly something to do with electromagnetic fields as well, in the sense that the charge is being produced by the movement of charge. So we have an electrostatic charge across the membrane being generated by movement of charge, movement of electrons, movement of protons, and so on, in pretty strictly defined ways. So there's a lot of information that you have in those about your state in relation to the world. So why would that give you useful information? I think it would give you useful information because if the whole thing was automated, and you respond to your environment by changing your phosphorylation state, by changing your gene expression, by upregulating chaperone proteins and a stress response, whatever it may be. So you're responding automatically to your change in state. How do you know whether that's going to be good enough or not? Should you have stayed or should you have gone?
Right.
And as soon as you start changing those things, you're no longer in the state that you were before. You're now in a different state. So have I done enough? Do I need to keep doing more? When do I stop? And how far have I come already if I can't remember the previous state that I was in? So you're messing up the situation all the time by changing in response to it. And so if you want to know how am I doing right now, you kind of need to have an immediate answer. Like, it doesn't have to be a perfect answer. It needs to be an approximate answer. I'm okay, stay, or I'm no good, go. In which case, a certain membrane potential is giving you that information before you've had a chance to respond to your environment internally. And if you can do something about it, like move, power up your flagellum, which is proton powered, by the way, and paddle over there, then you've got agency. You've sensed your environment. You had a physical response at the level of membrane potential that tells you how your metabolism is in relation to that environment before you had time to do anything about it. And that said, oh dear, power up the flagellum and paddle over there. So that state, that membrane potential, the electrical charges seem to give you this information and could potentially be the physical states that we associate with feelings. Obviously, they're hugely embellished in the central nervous system, and
Yes.
I'm not trying to explain everything here. It's just what is the physical basis underpinning it. It seems to me to relate to metabolism and charge and fields and those kind of things. And another kind of really interesting and important thing then about that is it relates to the wetware of metabolism. It relates to the survival of organisms. It relates to integrating your state in relation to the environment in terms of your wetware. And so an AI, even if it's even if it's robotic and self-aware and all of those things, is not necessarily going to have, it's a very different substrate. It's not necessarily going to have feelings in the way that I suspect animals would.
Yes. Your position reminds me of Anil Seth, who I think I've gotten most of my ideas about consciousness from. I think he nicely summarizes consciousness as a subjective experience of being that thing. So when a group of bacteria receive and they sense some stimulus in the environment and they react, are they reacting in a subjective sense? Are they all reacting in a similar way?
I think it's kind of inevitably subjective, and I kind of agree with Anil Seth, and also in terms of feelings and emotions and the difference between them with Lisa Feldman Barrett.
Yes.
And she makes a distinction between a feeling as a kind of very low-grade report, interoceptive report of bodily organ state, and an emotion as an interpretation of that feeling in the context of the cerebral hemisphere processing of,
yes,
oh God, there's a tiger over there, or whatever it may be, and you put the two things together and project into the world your state. You know, what should you do about it? So it's kind of interpretation of interoceptive signals, but the feeling then is those interoceptive signals reporting back on bodily organ state, which in the end is reporting back on the metabolic perturbation of those organs. And I like the way that Anil Seth thinks about this in terms of effectively a kind of Bayesian probability of this. Is this the right answer? Change this a little bit, do another take. Does it still look like the right answer? So you're kind of constructing the world that's out there by continually questioning what's out there. I think that this kind of approach is true of bacterial cells as well. I think the same. Maybe it's inappropriate to use the same words, but we don't have better words for it.
Yes,
so you find yourself
fails.
echoing the terminology of neurology to talk about a bacterial cell, which feels mad, but it's the same problems they face.
Yes. So then would you be comfortable in saying that bacteria are maybe not conscious in the same way that we are? They're definitely not conscious to the same extent, but there is, it's a spectrum of consciousness, and it's about how much consciousness, and they likely do have some subjective experience of what it is like to be that bacteria, even though to the human brain we can't empathize with that, we can't understand that, but it's likely that that's the case.
I don't imagine that they would have any self-awareness as such. The problem with consciousness is this, it means all things to all people.
Yeah.
And I'm not talking about consciousness in any way that most people would understand it as relating to a human being. But is there a kind of a quantum of a feeling in a bacterial cell trying to integrate its state in relation to the environment as a readout of your metabolic wetware, as a charge and movement of charge on a membrane? Yes, I think that they would have feelings in that sense, and it may be as simple as good or bad, go or stay. But I the question, the kind of bigger question behind it is, if feelings evolved, then what was being selected, and what is the simplest form that was being produced by cells or organisms anyway that was capable of being selected by natural selection? And as I said, if it's a physical state, then what is that physical state, and what is it telling you about your environment? So all of this, it's just thinking. I don't like the word speculation, because it is speculation, but it's testable speculation, and so it's hypothesis. Let's grace it with the word hypothesis.
Yes.
But it's kind of logic from what we know about how bacteria and organisms behave, and I was left. My impulse was to then say that consciousness, or at least feelings, are a property of all living things, but not a property of suns, and not a property. I don't really subscribe to the idea that the universe is conscious, to the kind of panpsychism ideas. I tend to think of it as primarily as a process of life, of living things, and dependent on the substrate of living things, so the wetware of metabolism and so on. But then you're still faced with this question of what does it do and what's it for and how does it get selected? And my answer to those is that, well, it's about trying to understand how you're doing in relation to the environment through a single readout that tells you immediately I'm doing well or I'm doing badly, which is a physical state of charge and fields associated with that charge. I don't know how cells are picking up on that and responding to that. It's not that I've not got an answer to half of the questions that these raise, but I think that way of thinking about it has the potential to say, well, here is the minimum possible imaginable feeling, I'm good or I'm bad. Here's what it is physically. Here's how it becomes incorporated into a more complex cell. Here's how you end up in the central nervous system and so on. And underneath it all, there has to be some correlation between what the organs are telling you about your state and your actual state. Just as with perception of a tree or a lion or whatever it may be, there is, even though we're projecting it and we're trying to conjure our understanding of the world into existence by projecting it out into the environment, we have an input of photons, we have an input of sound and whatever it is, and there's some objective basis, even if it's a very flawed objective basis. There is an input that we need to interpret, but it was a physical input.
Yes.
And I think feelings in that sense are a physical interoceptive input about the status of the organisms grounded in the metabolism of those organs. And then the question is, how does the system know how those organs are doing? What was the readout that said my kidneys are in trouble here as it feeds back somehow to the central nervous system?
I think that's a really cool mental model of consciousness that I haven't really heard vocalized in exactly that way. A single readout of kind of the state of the body. It sort of reminds me a little bit, I'm very unfamiliar with these ideas, like Karl Friston's free energy principle.
Yes.
That's what sort of rings in my mind, but I'm unfamiliar. Maybe you'd be better at sort of explaining that, because
I've discussed
cool ideas,
these things with Karl Friston and with people like Anil Seth. And yes, I mean, Karl does think about single cell, but mostly he thinks about the central nervous system, and he's a neurologist by training, but he generalizes the free energy principle down to the level of cells and even back to the origin of life. And it's quite mathematically complex.
Yes.
And it's not something that I've really tried to get to grips with in a very serious way, but at a kind of a superficial grasp of what he's saying. It's really about how does an internal system which is separated from the external system, that changes in the external world will change the internal system in its own way, and that is almost by definition subjective, because it's the internal system which is changing, and the change in the internal system, you need to project it back into the outside world to try and understand what did it mean? What did it happen? It's really very deeply built into the way I think that most neurologists think about how an organism constructs a kind of hypothesis as to its situation.
Yeah.
What environment am I in? Am I in danger here? Am I not in danger? And is it good or is it bad? It's very linked up, I think. It's a formal mathematical way of seeing that question. And I think it applies to cells. Yes, I think it applies to bacteria.
So cool. I'm also a huge fan of Peter Godfrey Smith's work on consciousness. Huge fan. Talking to him in a couple of weeks. I think he's done just his Other Minds as a book, I think, did an incredible job at expanding the consciousness conversation beyond humans. But he has a really interesting example. I'm really interested in this question of where is the line, and how as you get more complex organisms, how does consciousness become greater or lesser in different ways? And he has a really interesting example of an ant. One conscious experience that we share is if we both got punched in the face, we would react differently. If you did MMA your whole life, you would react in a very different way to me. So pain is a subjective experience. It's a conscious experience based on our past experiences.
Yeah.
And if you tear a leg off an ant, it doesn't actually seem to act in any way that's different. It seems to just be completely normal, according to Peter in his book, Other Minds, not an expert in ants. So that would seem to me that they don't have a conscious experience of pain, or at least in that way, or doesn't have a conscious experience of pain in that area, which is an
Having
interesting.
said that, I saw a picture, funnily enough, today just online. I've got no idea really any of the context of it, but it was a picture of an ant that had had its leg pulled off, and there was another ant that was effectively dressing the wound in some way. It appears to was it licking the wound? Was it putting some antiseptic down? I don't know what it was doing, and I
Wow.
don't know if this was a fair. But I just saw this picture and thought, wow.
Yeah, they do
um,
weird things. That,
is it in pain as well? I don't know. Not obviously, but it's
yes.
interesting that the other ant is obviously aware that it's lost a leg and is doing something about it, and this first ant is standing there and allowing it to be done. So there
Yes.
must be more understanding of that predicament than you would have just from a purely kind of unthinking entity.
My understanding is that they communicate a lot through pheromones, and you can sprinkle a pheromone that they release when they die onto a live ant, and other ants will come up and pick it up and bring it back to the nest and kind of bury it, or kind of have like some sort of burial ritual, even though the ant is actively moving and alive. So the pheromone signal they're receiving is overacting any. And they can also find themselves in death walks, right? If there's a circle of the pheromone, they can find themselves trapped in the circle, and they'll just walk until they die. So that they're just trapped in a signal which says like move forward, move forward, move forward, and they're just forever in this algorithm. So to me, that seems very limited consciousness. Those seem like algorithms. If this, then this. If the, that
Yeah.
seems like executing very simple steps, but perhaps it's conscious in ways that we don't perceive, and it almost certainly is.
Yes, I mean, I don't really have much to say to that
Yeah, I
beyond
just think
it.
it's cool. I just think it's interesting.
Yeah, I mean, there's obviously a fair amount of algorithmic behavior, but again, your perception of the world, your you've got some sense which is coming in which says this pheromone is overwhelming, this pheromone is a death pheromone, this ant is dead, and you also have the perception of your eyes that saying it's moving, and then you probably is there any processing going on? And so, well,
Yeah.
it's moving, but maybe it's in a death throw or something. It's definitely dead. The pheromone tells me it's dead. You've got some conflict going on there.
Yes.
You've got conflict between algorithms
Yes,
telling you
exactly.
different things, and one of them outweighs the other one. And you end up with that behavior. Is that a reasonable interpretation? I have no idea. I don't work on this kind of thing. But is it capable of feelings? The difficulty to me is if you say, no, it's not. It's too simple. It doesn't have any feelings whatsoever. Feelings arose later with a more complex central nervous system. And this is too simple a system to be able to have any kind of feelings at all. The whole lot is best explained in terms of an algorithm that is simply a deterministic response to a pheromone or whatever it may be. Then you're obliged to say, then feelings as we understand them are a property of a central nervous system and of a sufficient complexity, and therefore it's a property of complex neural networks. It's an emergent property of complex neural networks. In which case, then you're faced with this problem. Okay, so why does this network firing associate with a conscious perception and this one does not?
Yes.
And so we're back to the problem that I framed in the first place, which is that if you try and explain feelings as a property of neural networks, I don't think we're any close to doing it. And it's not just now. You go back to Christoph Koch and Francis Crick in the early 90s, or Edelman before that, talking about the neural correlates of consciousness.
Yeah.
And has that worked? I think the answer is no. We do not have a neural correlate that says this pattern of firing is associated with a feeling or a qualia of this or that or the other. And there was that famous bet with David Chalmers and Christoph Koch about how we'll explain consciousness within 25 years or whatever it was. And that was a couple of years ago. The 25 years was up. And they agreed that we don't know, that we're not there yet. So that is the approach of the correlates of consciousness and the neural networks and so on. I personally think it's the wrong level of analysis, but that then pushes me into the frame where I have to say that an ant is going to have feelings.
Yeah.
Maybe very, very little. They may have been minimized, but there still has to be some perception of its predicament, and that's going to be overwhelmed by the kind of the automated algorithms that say walk in a circle with this pheromone, or kind of things you were saying. But I've got out of this other loop, which is the problem that I don't have to explain feelings as a property of an emergent, an unknown, an almost unknowable property, emergent property of a neural network. I'm explaining it in terms of metabolism and charge.
Yes.
But by my very definition of it, it has to be present in all animals, maybe not sponges, but maybe not plants. I mean, again, a place where I definitely, interestingly, agree with Peter Godfrey Smith, because he would limit it to animals, but also to motility, to the ability to move around, to be able to change your environment. And that's what I was saying about bacteria as well. Power up your flagellum and move over there. I don't think we would be very far apart in that. I think, there isn't a line, there is a continuum.
Yes.
And that continuum is really about, can I act on this set of charges? Those set of charges are inevitable. You poison your environment, you will change your metabolism, you will change your membrane potential. The question is, can you correlate with that something meaningful, and can you do something about it? And I think the only meaningful thing you can do about it is to move.
Yeah.
And that would have agency and consciousness linked with movement. And therefore, again, the necessary prediction of that hypothesis is that plants are not going to be conscious. Even if you can anesthetize them, they're not going to be conscious. So that would put me out of joint with a lot of people who would love to see consciousness as a property of all living things and not the universe. I don't know. I mean, you try and come up with an explanation as a hypothesis, and it forces you into a corner. It forces you to say, okay, well, if this is true, then that has to be untrue, and this can't be right, and so on. And then it's testable, at least.
Yes. I've had the joy on the podcast of hearing just completely different perspectives on consciousness. I spoke to Dr. Robert Prentner, who's a colleague of Donald Hoffman, who believes consciousness is fundamental. The universe is created through the interaction of conscious agents. I don't understand that at all. I think I resonate a lot more with Anil Seth and your view that it's life based, it's material. I always assumed my whole life, I think wrongfully now and naively, that it was an emergent property of complexity. I think I read this in Being You, I think is a great argument against why that's not the case. Is our cerebellum contains about half of the neurons of all our total brain, yet it doesn't seem to be involved in consciousness at all. So I thought that was a really interesting piece of evidence for why just neural network complexity isn't probably where you just get this emergence of consciousness, that it's more likely some specific ingredient list, and then you get a number of things that come together rather than just meshes of information, and then you just for some reason get this categorical step shift in change. With your view on maybe this underemphasis on metabolism and electricity with consciousness, how do you think we should be studying consciousness? And I know this isn't your area. We're at the end of the podcast, so we can be more hypothetical. We can speak more liberally. The people that are here for the long haul. We can even just. I know this isn't your area, but out of curiosity, what does metabolism-first consciousness look like?
I mean, what I'm actually doing is using fruit flies. And I've got a couple of people in my group who are looking at anesthetics, and we're trying to actually at the moment just use fairly conventional molecular biology to manipulate electron transfer in the respiratory chain and look to see how does this affect anesthetics and susceptibility to lose consciousness.
Right.
So
very cool.
A lovely phrase from Luca Turin that nobody could agree whether or not a fruit fly is conscious. But most assuredly, anesthetics will make it unconscious.
Yes.
So you can make these things unconscious, and we can try to see if we manipulate the rates of electron transfer, does that change the sensitivity to anesthetics? And can we prize apart these two possible explanations? One of them is it may be just to do with ATP and energy availability, and what anesthetics do is effectively take away the energy to have a complex neural net functioning at all, and so you have a synaptic power failure. So there's kind of a simple and probably quite elegant and probably reasonable explanation for it.
It's fascinating.
But the alternative is to do with the fields themselves, which is, I think, a lot more problematic, but a lot more interesting if it's true. And so the question is, can we distinguish between those two? And if we end up that we can put it all down to ATP, well, that's something worth knowing. If we can say definitely that anesthetics work on mitochondria and do this, that's definitely worth knowing. But if it turns out that there is something to do with the way that mitochondria generate electrical fields that tells you how you're doing in relation to the environment, and now only this bit of the brain is responsible for reporting back on that, but in that bit of the brain you've got this morphology and it behaves in that way, then I think only if the standard molecular biology tells us that it's really not it really is explicable for mitochondria, it's really not about ATP, it really does seem to be about fields, then at that stage, I don't want to try and measure the fields. Until then, I'm not going to go near it because it's just too difficult, and it's a great way of trashing your own career.
But as you said at the start, it's a question that's too interesting not to ponder. So when you have the opportunity to go do some interesting research that could shed some light on it, it's who cares about your career to some extent,
Yes, I agree. I mean, I'm kind of joking, but I mean, there's also some truth to it. But it's not that I care about my career.
Yeah.
But I want to be a good scientist. I want my science to be meaningful.
Yes.
I don't want to kind of blindly kind of blunder around in the undergrowth where it's not possible to come up with a reasonable scientific answer that other people would be able to criticize and reject or accept. So in that sense,
I understand.
If I kind of blindly go in and try and measure fields and come up with answers that everybody else says no, that your measurements are wrong for this reason and that reason and whatever else, and you end up in a sterile debate with bad measurements that are hard to make. I don't want to end up there. I think there's a lot we can do with molecular biology to narrow down the question and say whether or not anesthetics really are primarily working through inhibiting electron transfer in complex 1 of the respiratory chain, or if it's really not that.
Yeah.
If it really is what the mainstream field would say, it's about GABA receptors, it's about the activity of neural firing, it's about NMDA receptors and so on. If we can show it's not that, but it really is about the mitochondria, then it's, to me, it's just exciting questions. It's exciting science. If it's not that, well, it was fun trying.
Yeah. I do wonder, does science need a bit more experimental research that isn't strictly hypothesis driven? I think there's some drawbacks to strictly hypothesis driven experimentation where you have you've rich boundaries and constraints, and that kind of biases your thinking in a lot of ways, and you have sort of a strict page that you can operate on. Experimental research surely opens up a lot more area to be creative, to be instinctual, to follow things that kind of have some indication, but maybe you can't write out a full, a grant application to do it, and I think there's a lot of...
I think this is actually where hypotheses are most useful. It's not that the hypothesis has to be right or wrong. It's just that, okay, this is what we know about the system. How could it possibly work? Well, it could work this way or it could work that way. And now we have two hypotheses. If it works this way, then this should happen if we do that. And if it works this way, that should happen if we do this. And so now you have an experiment that you're going to do. I'm going to try and manipulate this then and see what happens. Then it turns out, well, you manipulated it, but it didn't work properly for this reason. And so you end up having to do that. And you drift around the place and you end up getting lost. But if you want to come up with an experiment that's going to tell you something which is interpretable, you're back to a hypothesis. And the other thing that strikes me interestingly now, I'm kind of a little bit behind on AI and how to use how to use it in research in relation to these kind of questions. I don't have that kind of computational power. I have other strings to my bow, but that's not going to be one of them. And so there's an interesting question about what is AI going to do badly? What's it not going to predict? And this is something about the creativity of the thinking.
Right.
And at the moment, it's not doing that very well, as far as I can tell.
Yeah.
That's not to say it's not going to be doing it in 3 years' time. I've got really no idea. But this creative leap into the unknown, which is what a hypothesis is, that says, I think the answer's here, and here's an experiment I'm going to do to test it. That's something at the moment that is still a very human pursuit. Whereas if you're looking for patterns in the data, you're much better training an AI on it and finding those patterns and interpreting those patterns that way. But what it's going to tell you is everything you knew already with a much finer grain. It's not going to tell you the stuff you didn't know that's over there somewhere. Those patterns, there just is no data on many of the things that I'm talking about.
Yeah.
We don't know what the orientation of mitochondrial crystals are in specific neurons when we are experiencing feelings. Are they lined up? Are they generating a field? It's too small to see in native neural tissue. We can see it by cryo-EM, but then we fix the tissue. We can't see it with super resolution microscopy. Do we know what the actual membrane potential is? Do we know how it changes? We can't measure that properly yet either. So there's no data on it. So AI can't see that data and come up with an answer because it's just a void where there could be some information. So can we generate some of that data? The answer is, well, a lot of it not quite, but maybe in a year or two, super resolution microscopy will be good enough that in a tissue we can see the orientation of the crystal membranes in the mitochondria. Do they move around like wheat in a field with a breeze, and then occasionally kind of orientate and vibrate for a second or two, and then go back to waving around? There's so many imaginable things that could be happening that we've never seen.
Right.
Is that what's going on underpinning feelings? I would like to think so, but you're not going to be able to use AI to parse that data in an objective way and find an answer that way. We're going to have to be more creative about it, I think.
Yes. Have you thought much about the future of AI and science and really where the huge advancements could occur?
Again, I don't know. I don't know enough about it. And the places where it seems to be already making a huge difference is where we have very good, high-quality data that's difficult to see where the patterns are.
Yeah.
So, I mean, I could give one example where it could make a huge difference, and I think people are beginning to think about these questions. So, mitochondria have their own DNA, and that DNA is coding for the respiratory proteins, and those respiratory proteins are part coded by the mitochondrial DNA and part coded by the DNA in the nucleus. And so every generation, every individual ends up with a different combination of a mitochondrial DNA against a different nuclear background. But when we do, let's say, GWAS studies, so these are genome-wide association studies, which letters difference in the whole genome are associated with epilepsy or with Parkinson's disease or whatever it may be, you look at all these things in the nucleus, you ignore the mitochondria, you just throw that away. Or if you look at the mitochondria at all, you look at mutations in the mitochondria and say, these mutations are associated with this condition, a little bit more risk of Parkinson's disease or whatever it may be. But what we're really looking for is the interaction between these genes and those genes.
Right.
And that's missing.
I didn't know that. That was missing from the picture.
Yeah. I mean, GWAS usually bin that. Now, a lot of the time, it may be possible to unbin some of that information. This is the kind of place where we can do experiments in fruit flies and we can show that if you mismatch the mitochondrial DNA to the nuclear background, it can affect lifespan or fertility by 30, 40, 50%.
Wow.
So the scale of the effect is big. And these differences are likely to be the differences between individuals as well. And how would we respond to medicines? And how would we respond to a diet or to exercise or to aging just generally? The interactions between the mitochondrial genes and the nuclear genes are likely to underpin a lot of that variation between individuals. But at the moment, we have no data on it. But in principle, we've got uncover all of those mitochondrial DNAs and then set AI to work on this problem and effectively say, okay, you are at higher risk of this and you're at lower risk of that because you've got these, you've got this good combination of interactions, you've got that bad combination of interactions, whatever it may be. This is just variation between individuals, but it's largely unlooked at. So AI could be extremely good at doing that. But I'm not the person to do it, unfortunately. I wish I was. But
why has that data been thrown out in the past? We didn't have the data analytic tools.
Treated mitochondrial genes as basically trivial. There's only kind of 37 genes in the mitochondria. There are 20,000 genes in the nucleus. They're kind of labeled housekeeping genes, which is a bit of a derogatory term.
Yes.
And they're considered to be kind of neutral. They've been used to track human evolution, but going back to mitochondrial Eve, on the kind of the understanding that they're not under strong selection, which is completely wrong. They are under strong selection, but they behave oddly. They behave as if they're neutral. Some of them do. And there's a kind of a deep tension about how that works.
Interesting.
And part of the answer is, well, the mitochondria have to work differently in males and females because we have different types of metabolism. They have to work differently in the brain compared to in the kidneys, compared to in the muscles, and so on. They have to work differently if you change your diet. So they have to be kind of quite generalist, in fact, in how they behave. And this is why it looks as if they behave neutrally. But if you have unfortunate mismatches between the way the mitochondrial genes work and the way the nuclear genes work, then it can have catastrophic effects on the system. We can see that in the fruit flies. And we know that clinically as well. So these are places where I think AI will make a huge difference.
Right.
But again, someone needs to be smart enough to say that's where the question is. And as you say, most people have not really registered that that's where there's a problem. It's they're focused on the nuclear genes because there's 20,000 of them, and you can apply your current kit to ask that question. And you can't apply your current kit to ask the question about mitonuclear interactions. You can't just do GWAS. You need to start thinking about the interactions between things, and that's known as epi-GWAS. And in principle, you could do it, but in practice, I don't know that anybody is doing it yet.
It's hard. Wow. It seems astonishing to me that early scientists would label it as something like housekeeping genes with such hubris. Like it's very overly confident that they don't do anything, and it's kind of dooming future generations to also assume they don't do anything by virtue of that name.
There's so much in words, in names, that and we go through an education system and it tells us these things, and we kind of passively absorb it without questioning it.
Right.
And it can really frame the way you see the world and prevent you from asking the right questions.
Yes.
So it's
for sure.
Words are really powerful things, and they really shape and color the way that we see things. And I suppose writing books, I think a lot about words, and I've written very colorful passages that I'm very pleased with, and I look back on them and I think this is a nice metaphor, but is it real, or am I deluding people, then deluding myself with this metaphor? A nice easy one would be reactive oxygen species as being kind of thugs and hooligans that go around throwing bricks at DNA or RNA and damaging proteins. But they're quite subtle signals. They're not that reactive. I've painted a picture of them because it's easy to write and it's fun to read. And but is it real? And the answer is, well, I probably went too far there. I may have been misleading.
You need to bring science to life. You need to bring science to life. I think people don't place enough emphasis on making science enjoyable, engaging, interesting. If it deviates a little bit from the bounded definition, then getting twice as many people excited about it, I think that's a trade-off that's worth it 1,000 times. I said at the very start that your writings have been a huge inspiration for me as a scientific communicator, because they were like poetry. It's the same thing. I read Carlo Rovelli. I'm not sure if you're familiar.
Yes, I read
Stunning writer. Really, really primitive, really building all of the inspiration that I have now as a scientific communicator, reading those words and how he talks about quantum mechanics. And I don't even understand a tiny percentage of what's in that book, but it's just it gets me so excited about ideas and so interested in science that I think that's unbelievably, just important for me in my life. And your books were the same. I think Richard Dawkins, the first time I read The Selfish Gene, is the same, just in terms of a categorical shift in how I think about things. And this conversation has been so much fun. I'm so excited to. Do you have any more books in the works? Are you working on anything at the moment?
I've not started yet. I have a contract to write a book and deliver it in about 1.5 years' time, so I better get going. It will be on the origin of life, and it will be from effectively prebiotic chemistry to cells with an agenda. That will be the subtitle as I have it at the moment.
Interesting. How do you plan on making it different to the books that you've already published?
Well, you could be harsh and say they're all on the same thing anyway. So I've never addressed the origin of life as a full question. I've always had chapters on it. And those chapters have been about prebiotic chemistry and the structure of cells and proton gradients driving the beginnings of chemistry. I've never written anything at any length about where does the genetic code come from? How do you get to the ribosome? How do molecular machines get going? How do you end up with cells that are capable of living independently of a hydrothermal? So the whole process from one end to the other end, that's the challenge. There's a few gaps in there that I'm not going to be able to answer, but I want to lay out, here is a story. I want to be honest that it's a story. We start with CO2 and hydrogen, and we go through to cells with molecular machines and genes and selection as we know it, and some sense of agency and possibly feelings where we end up with these. What are the necessary steps to join all of that up? What's being tested? What looks persuasive? What looks unpersuasive? Is it the only route between these two places, or is it possible to imagine other routes? So full on, I want to give it my best shot to answer this long continuum of the origin of life, from really simplest chemistry to real cells.
I'm so excited to read it. When you're thinking about a book, do you read broadly science, like popular science? Do you read broadly across different topics to try and get inspiration about how you want to write your book and the kind of ideas you want to bring in and the level of depth and level of analysis?
The honest answer to that is no. I read quite widely anyway.
Okay.
But not with any intention to mimic it or to write it that way. I have cautionary tales from my own writing. I mean, my last book, Transformer, I'm very pleased with it. I'm very proud of it, but it's a hard read for people who are a little bit intimidated by metabolism or by chemistry.
Yes.
I think I wanted to do it that way, and I wanted to pay tribute to the pioneers, but I think I lost a lot of people who thought I went into too much detail and would rather have a kind of broad brush analysis of what does all this mean then? I don't need to know about the structure of succinate and how it becomes alpha-butyrate. I want to know roughly what's happening with the Krebs cycle. Yeah. So I failed to do that, I think, for a lot of people. And it did what I wanted it to do, but I think it was a book that some people love and some people found really quite hard work and not so much fun. And I think this next book on the origin of life cannot be as dense as that. I need it to take a step back and go back to more of a broad brushstroke. I'd want the level to be probably closer to the vital question, but it's going to be in more detail because it's really on the origin of life alone, and the vital questions strayed all the way across eukaryotes and sex and all kinds of things as well. So this is going to be nailed on the origin of life, but with bigger questions about where does genetic information come from and how does it get going. Yeah. So it's not a case of I want to read other people and think how to do it. I know the pitch that I want to get, the level I want to get, and I want it to be a level up in terms of the chemistry, more of a big picture take, but with enough detail there's enough flesh there that it doesn't look like hand waving.
Yes. I think it is the ultimate difficulty as a scientific communicator, right? To figure out what level of analysis to discuss your topic on, because there's infinite levels of analysis and each will widen the net or closing the net, and being ultra specific and ultra detailed will resonate hardcore with the aficionados, and you'll lose a lot of people. I don't know if there is a right or wrong answer to it. It's just it's the complexity of being a communicator.
You just have to fight your way through it and hope that you get the right level, and that it's, as you said before, entertaining as well as informative.
Yes.
It's really, you can't just be dry through that material.
Yes. I think it's the biggest issue is people trying to be too dry with their science and not focusing enough on just getting people excited, interested, and curious.
Yeah.
Who are some of your favorite science writers?
I mean, I have to mention Richard Dawkins pretty high up. I read The Selfish Gene when I was 16. I can't say I liked it. That's not because I didn't like the writing. He's a magnificent writer. I found the ideas at the age of 16, I won't say repellent, but horrifying. I think that's exactly what he wanted me to feel. He wanted me to feel viscerally, I think that's a phrase he used somewhere, that this is right, that this is how the world is. And I didn't want the world to be that way, but I didn't have any good arguments against it. I then read a book by Stephen Rose and a couple of other people called Not in Our Genes, which was more or less an attack on the selfish gene. And I could see all kinds of holes in their argument, but I felt relieved that there were arguments against it.
Yeah.
So it was really, in that sense, it was a world-defining book for me. And I think I've always had at the back of my mind his clarity as a writer, his ability to get across ideas, not just so you understand them technically, but that you just feel the strength of the argument.
Yes.
I've always really admired that as an apotheosis of what science writing can be. There's all kinds of other people. I was very influenced for a period by John Emsley. I've not read so much of his stuff recently, but he has a wonderfully conversational tone about chemistry.
I'm not familiar with him.
Yeah, well, he writes about chemistry, but it's almost a chat, and he's able to make it very unthreatening and very conversational, very interesting, full of tidbits. And I tend not to write that way, but I aspire to be able to bring something of that chatteriness, of, sitting in a bar or a pub or a cafe or whatever, and just having a conversation. He has that, which I admire. Carlo Rovelli, you mentioned the poetry of it. He has an amazingly poetic way of writing. And again, it's very interesting that the poetry is partly in the words, but it's not really translated. It's in the ideas. The poetry's there in the idea, and he has a wonderful way of writing. But the poetry is really in what he's saying. It's not in the actual words. And there's a lesson there as well. In fact, a lot of thing about writing is it's not in the words so much as the ideas and the pacing. And there's all kinds of there's interest in writing which is beyond the choice of words that you use. And Rovelli is a very beautiful example.
It's just a rhythm to his writing. I feel like it was just a rhythm. It flowed. Like it was one of those. It was just impossible to put down. Like because it just flowed from sentence to sentence. And you just wanted to keep reading. Yeah,
I mean, going back, people like J.B.S. Haldane wrote amazingly with a kind of muscular common sense, and he would, but just a great clarity.
Yeah.
Peter Medawar was a wonderful writer. A little bit stuffy at times, but with an intellectual incision that kind of just infuses everything that he wrote. So I mean, there's a lot of people who I really love their writing.
Amazing.
Frank Harold, who died recently, has written several books which are about early evolution and cells and biochemistry and the kind of things I write about. And it makes you realize that very few people actually try and write about those things.
Yeah.
And he did so with a combination of an almost religious sense of majesty about the scale of what he's trying to explain, combined with a kind of a folksiness, which again undercuts the poetry of it. So it's kind of interesting. I admire all these things about different writers, and I sit down and write some stuff, and whatever I write it doesn't look like them. So I think you can't help what you write, but you have all these influences, people you read. I'm reading Matt Ridley at the moment, and again, he writes beautifully, but very plainly. And the interesting thing about that, to me, it reminds me a little bit of I'm forgetting his name now, the novelist oh dear, I'm sorry, I'm completely forgetting his name.
No worries.
Who wrote books about Pompeii, among other things, and it'll probably pop into my mind right after we. And anyway, what I wanted to say is they are both extremely good at taking themselves out of the picture. You're not faced with their style between them and the reader. Somehow they're extremely good at interfacing directly with your own mind.
Yes.
So that somehow you're not thinking, oh, I'm not sure about the style here. You're not primarily conscious of the way they wrote it. You're primarily conscious of what they told you. It's almost as if there's a direct transmission of ideas into your own mind. And it's not an easy thing to do at all. And Matt Ridley is extremely good at that.
Right.
There's so much to learn from people. And it's such fun trying to convey these ideas.
100%. That's why I wanted to ask you. I thought you might have some good scientific communicators. I hope to write a book at some point in the future. And again, I really can't stress enough again how appreciative I am for your science communication work. I think you've touched so many tens, maybe hundreds of thousands of people and inspired them to go on to be the next generation of scientific communicators. So I want to thank you so much. This conversation has been so much fun. I've learned so much from you. I've really, really enjoyed the whole thing. The way you communicate science is amazing. You clearly still have a childlike enthusiasm towards the ideas. Like you can see yourself in the chair. You're getting giddy and moving forward, and you're smile. Like you can tell you never lost that childlike enthusiasm. So I hope I'm the same. I'm just so grateful. It's been so much fun. Thank you so much for everything, Nick. I really appreciate it.
Pleasure. Thanks a lot. Bye now.
Thank you so much for watching to the end of the video and supporting the channel. We've seen a lot of growth recently, and I have all of you to thank for it. I absolutely loved this conversation with Nick Lane, so I hope you enjoyed it as well. If you want more, then I couldn't recommend more my episode with Anil Seth and Peter Godfrey Smith. We go way more into consciousness, subjectivity, insane, amazing. Thank you so much. Subscribe to the channel, and I'll see you next time.